subjects. Welcome to the HSC Physics Headstart lecture for 2023. Just off the bat, I'm really sorry that this couldn't be a live lecture. Unfortunately, I'm just not available. But we can still have a little bit of fun through a good old recording. It should be a good little bit of a time. We should still have some fun. And speaking of which, before you, I don't know, go ahead and skip the video, just a couple of things that I want to hit right off the bat. Immediately scroll down below this video, and even though this isn't a live recording, I've still set up a whole bunch of questions for you throughout the lecture. So even though it's not a live recording, and so I'm not able to like immediately see, you know, what you guys are answering to my questions, you can still answer them, and at some point I will go and check out the answers and see, you know, how you went with different questions. Because that's just like something that I like to see. I always like to see how you guys are doing. So yeah, scroll down and you'll be able to access all of those questions. You should be able to see them down below. While you're down there, you should also be able to see a lovely little tab that says resources, and so you should be able to access anything that I talk about throughout the lecture. And also, if you take a look at these slides and you're like, you know, maybe I actually kind of want to like have a copy of these slides for myself, whether it be to like follow along as we go through, or just for reference later on, because I like to think that this is a good summary. I've made my slides. I like to think that my slides are pretty decent. You can go ahead and download them down below. And also, evidently, this thing is being recorded, so you can come back to it anytime and watch it back over again. But without further ado, let's just jump into it then. I also just realized my headphones aren't even plugged in, but the audio was working beforehand, so it should be fine. So I don't need them. But before we jump into anything else, you might be wondering, who are we? Who is ATAR Notes? Well, ATAR Notes is a group of we are a group of past students, and we have come together to try and help you guys, the present students. I mean, like, we've all done our HSCs, and most of us have done we've all done decently well, so we want to help you guys to do the absolute best that you guys can as well. And so one of the ways we do that is by offering a whole bunch of free resources for you guys, right? You can head over to our website, atarnotes.com, and you can get access to a whole bunch of study notes. You can get access to these lectures. So even though this one may be recorded right now, if you're watching this around about that like third week of January 2023, we currently have a whole bunch of live lectures as well. So that's for like tons and tons of different subjects. So even though you might be at the physics recording, you can go and check out the lectures for chemistry or maths or English or biology or like history or whatever subjects you do. You should be able to find some lectures for those as well. You can also find a wonderful forum over there where you can have all of your questions answered by our wonderful past students or present students, the best of the best. We also have a whole bunch of resources to sort of help you to do the best you possibly can, and kind of cheeky little explainers maybe for tricky topics and all that. We have a weekly newsletter you can sign up to. Highly recommend. It keeps you up to date on any dates, whether it like and things that are going on in the world of the HSC. You know, if you've got like scholarship deadlines coming up, whether it be university applications, that sort of thing. It will show you when all of those things are coming up. Of course, we've got our classic ATAR notes, classic ATAR calculator. If you want to know, see how you're doing, see how you're tracking. We have some articles that you can check out just about like different topics, and of course, we've got a whole bunch more that you can check out. So head over down to atarnotes.com to check out all of those resources. And on top of that, we also have a couple of paid resources as well. We have our incredible tutoring program, TuteSmart. We've got a whole bunch of really incredibly well-written study guides and topic tests, and the classic Ed Unlimited. But I will chat a bit more about those when I get to them later on, which should be a whole lot of fun. But of course, before that, you might be wondering, who am I? Who is this guy who's chatting you at the screen? Hello, my name is Tim. I am the physics tutor here at ATAR Notes. Physics is my game, and normally I am having a lot of fun just doing these lectures live. Unfortunately, I couldn't do that this time round, but hopefully next time in May or April, April probably, I'll be back with another live lecture, but it should be good. I graduated from the HSC in 2020 with an ATAR of 99.75. I did 4-unit maths, physics, chemistry, and Advanced English, and I'm currently studying maths and quantum engineering at UNSW, which is a lot of fun. So if you have any questions about like maths or like if you're one of the like vaguely interested in maybe studying engineering or something like that, chuck a question. I don't know if there's a Q&A link below, but I'm gonna be checking it out when I get a chance. So hey, I may be able to get back to you, if you are interested in that. In my free time, I play a little bit of Minecraft when I have time, but I also really, really enjoy running, like long distance endurance running and trail running. I guess I'm just a little bit of a masochist, but trust me, it's actually a lot of fun. Trust me, bro, copium. This is a picture of me finishing the Sydney Marathon last year, which was a lot of fun, very hectic, very cool. I like running. It's basically half my personality. It's a good time and I enjoy it quite a lot. So the plan for today's lecture is we're going through module 6. We're going to go through electromagnetism, which should be a good lot of fun. Now I've split it up vaguely into two blocks, block 1 and block 2. Where block 1 we're going to go through the first two topics, 2.5 topics ish. So we're going to go through charged particles in electric and magnetic fields. We're going to go through the motor effect. We're going to go through electromagnetic induction, and then block 2 we'll go through physics study tips, applications of induction and motors and generators. Now, even though this is a video, I do encourage you to have a break between the two blocks, because sitting down and trying to absorb an entire module in the course of 2.5 hours is not a very easy task and not something that you're going to just be able to do like that. You need to give your brain some breaks. And in fact, that's one of my tips that I'm going to be talking about, is that it is important that you don't just go at 100 all of the time. It is important to take some breaks here and then. But yeah, that's what we're going to try and speed run as much of module 6 as possible. I've got a lovely little tracker bar down the bottom of my slides. I'm very proud of this. Okay, you can follow along which topic we're in, which should be a lot of fun. Now, physics is all about actually practicing. So pretty much the entire lecture, I would say about half of our time, more than half of our time, to be honest, is going to be spent actually doing questions and practicing the stuff that I'm talking about. And of course, one of the best ways to get the most out of this video, out of this lecture, is to work through the questions with me. So every question that I'm going to be doing in this lecture, like I mentioned at the start, I've actually given it to you guys. So if you scroll down below, you should be able to enter in your answer, and I'll be able to see once you do it, which should be a whole lot of fun. Yeah, so please do the questions. It will mean that you actually start to like try and practice the questions. I encourage you, if you want to challenge yourself, you can kind of pause the video wherever I get up to a question, and you can try and give it a crack yourself. If you don't have much of an idea of what's going on, maybe you just wait until I start a couple of steps, and then you can pause it again and then try it again, give it another answer. I mean, like, it's very low stakes, all right? If you get the answer wrong, it's not even live, all right? So I'm not even going to be immediately seeing that you're wrong. You have time to change the answer afterwards. Okay, so just give it your best crack, right? Try all the questions, try your best, and it should be a lot of fun. So yeah, without further ado, let's just get into module 6. Now, just as one last overview, I haven't just winged these sections. Module 6 is separated into 4 different subsections. Our first thing is electric and magnetic fields. Our second topic is the motor effect. The third topic is induction and its applications, and the last topic is motors and generators. So I've split it into 5 sections. Like, I've kind of kept the electric and magnetic fields, I've kept the motor effect, I've kept the induction, and I've kept the motors and generators. I've just sort of separated out that application section because the induction is a pretty beefy topic. So sort of, in terms of my topics, and also to have that like 2 topic split, I've sort of separated out into induction and then the actual applications of induction, which should be a lot of fun. But yeah, so electric charge is a property of our subatomic particles, right? So when we talk about that, right, in our last module, module 8, we'll take a really in detailed look at what the atom is. But subatomic particles, the atom is made up of protons, neutrons, and electrons. And all of those properties, all of those particles have electric charges, right? So protons are positively charged, electrons are negatively charged. This is all probably stuff that you learned before in year 11 if you remember it. And if you don't, well, hey, it's a good refresher. Now, a couple of quick things to note, because this is what we're going to be focusing on in this topic, is looking at the actual electric and magnetic fields and the forces associated with them, which is that all things that have a charge are surrounded by an electric field. This is very similar to how all things that have mass have an associated gravitational field. So it's sort of like, you know how you may remember if you've done the gravity topic, that like anything that has mass attracts any other thing that has mass through like the gravitational force, right? Which is why if I drop something, it falls to the ground because the mass of the thing I drop is like getting attracted to the mass of the earth, and that's how they attract each other. But the way that they do that is every single thing that has gravity has a gravitational field that is coming towards it, right? It's pointing towards itself in nice, neat, straight lines so that it pulls everything in the surrounding universe towards it. In a similar way, anything that has electric charge has an electric field surrounding it. And once again, it's nice, neat straight lines pointing in towards itself. The only difference is, unlike in a gravitational field where no matter what the object was, it always had the gravitational field lines pointing in towards it, with an electric field, it depends what polarity your charge is, right? So if you've got a positive charge, the field lines point outwards, whereas if you've got a negative charge, the field lines point inwards. So it's important to keep note of that little subtle difference between electric and gravitational fields. But aside from that, like they're basically the same. Now, only other things that have a charge will experience electric forces, right? So when you have two things, going back to my lovely analogy of gravity, right? I love the gravity analogy because they're basically like, they're very similar things, right? Um, if you have two things that have mass, when their gravitational fields intermingle with each other, you get a gravitational force as a result. And so those two objects will start being attracted towards each other. And so as a result, they'll start being attracted towards each other. And in a similar manner, when the electric fields of two particles start to interact with each other, you get a force as well. The key difference is, of course, once again, whereas with our gravitational fields, they were always attracted towards each other, with our electric fields, it sort of depends on our polarity. So if we have a positive charge and a negative charge, and those two electric fields interact with each other, if they're opposites, because they're opposite charges, you can sort of imagine the positive charge, which is having a force going outwards, meets the electric field of the negative charge, which has a field going inwards, and that creates an attractive force, right? Because the positive charge gets attracted to the negative charge and so on and so forth. Whereas with our positive charges, because they're both going in the same direction, they kind of start fighting with each other, right? So here's our positive charge, it's trying to be attracted in that direction. Here's our positive charge, it's also trying to be attracted in that direction. And so as a result, they sort of don't like each other, and you end up with something like that, where it's just gross and they don't like each other anymore. However, it's only experienced by other things that have a net charge, which is why, there's tons and tons of electric fields around me at all times, because like the net charge of me is not particularly great, I don't experience those forces. But that's why sometimes, you might rub your like hair with a balloon and it will experience some sort of electric attraction towards the balloon because you've like given it a net charge or whatever. And that's how that works. Now, as a quick bit of revision from year 11, we actually know what the formula for the electric field force is. It's F equals EQ. Now, your formula sheet, just quick side note as well, if you haven't looked at your formula sheet yet, or if you're not quite familiar with your formula sheet, just chuck into Google year 11 HSC physics formula sheet. It's kind of weird. It's like the second result that comes up now. Don't click on the first result because sometimes it can be a little bit dodgy, but just go to the one that looks like it's by Nessa. Um, Look it up. It should look like this. It's got all of your formulas. Actually, this one's looking slightly dodgy, but basically, it's got all your formulas on it, and it has the periodic table and all of your data on it as well. Now you can see over here, our electric field force is given down there by that E. Actually, that's one of them. Our other one is down here, E equals F on Q, which can be rearranged to the form that I kind of prefer it in, which is F equals E times Q, which is gives us the electric field force. You may or may not remember it from year 11. You touched on it from in year 11, but like this is now when it's actually going to be important. Now, the force acts in the direction of the opposite charge. So, for example, if you've got the force acting on a positive charge, it will direct it towards the negative charge. If you've got the force acting on a negative charge, it will direct it towards the positive charge. It's just sort of like that's how these things get attracted towards each other. Now, there's two different ways that you can express the sorry. Um, so the force is expressed in newtons, our charge is expressed in coulombs, and our electric field force is a bit of a funky one. It can actually be expressed in either newtons per coulomb, which comes from the fact that the force is in newtons and the charge is in coulombs. But there's actually another equation for our electric field, which is our electric field is equal to the voltage divided by the distance between. Now this occurs for a very specific scenario, which is when you have two parallel plates. I say specific, it comes up a lot, but it's like you couldn't use this formula, for example, a charged particle. Like if you just had a single charged particle chilling by itself, like you wouldn't be allowed to use it there. But if you have these two parallel plates that are next to each other, and you've got like electric field going from one plate to the other, in this specific circumstance here, you can calculate the strength of the electric field by the voltage on either of these plates and the distance between the two plates. And in this case, because these two formulas both calculate our electric field, you can also express not just our electric field in terms of newtons per coulomb, you can also express it in volts per meter because our voltage is measured in volts and our distance is measured in meters. So that's our formula, that's how we calculate it, and it's our first formula for today. It's on our formula sheet. Yeah, if you don't remember it from year 11, chuck it in your brain now. It's a good refresh. I mean, that's why we're doing these lectures, right? Because you get to sort of refresh yourself before the term has even begun on what we are doing there. So let's do a quick practice. Don't forget, down below in the little Slido poll, you should be able to give it an answer. So if you want to go through this question by yourself, feel free to pause. If you want to go through it with me because your brain is currently dead, don't worry, I feel you. We can go through it together. So in this one, we're going to calculate the magnitude of an electric field force on an electron positioned halfway between two parallel plates with a voltage of 10 volts between them, positioned 5 millimeters apart. So as with any calculation question, usually the first thing we want to do is just write down like what is all of the information that we're dealing with here, right? So the first thing is we have a voltage of 10 volts, and we're also told that our two parallel plates are positioned 10 millimeters apart. Another quick side note, another good thing to do at the start of a question is always to draw out a diagram. Sometimes it depends which order you want to do things in, but just for the sake of like, because this is a fairly simple situation, I'll just quickly draw a diagram. Now this is the specific scenario I was talking about beforehand, where we have these nice two parallel plates that are producing some kind of electric field. Sorry, that's what I'm like drawing here. I'm drawing the electric field lines because they go from positive to negative, right? And if you're curious, sorry, I've been saying that this is like a niche situation. The reason that this niche situation comes up so much is because this is the way that we generate a nice, neat, uniform electric field. So if we want an electric field that isn't changing over a particular like situation, because one of the annoying things with having like a charge that's producing an electric field is that it changes really, really quickly. Not to get like too far sidetracked, but if you remember back to module 3 in year 11, you would have looked at the inverse square law. Well, the intensity decreases essentially by the same kind of idea, whereas over here it stays exactly the same, which is why we like it. But yeah, so even though it is like the formula only works for this one specific situation, but this one specific situation comes up so much that it's like worth actually knowing what the formula is. Is basically what I'm trying to say there. That all aside, let's actually jump into the question. I'm sorry. This is one of the things, if you've never been to a lecture with me before, sometimes you'll find I make my own way, all right? Sometimes we get on a little bit of a sidetrack, and hey, it is what it is. We have a little bit of fun. That's what physics is, all right? At the end of the day, it's a little bit of fun. Now, our distance is 5 millimeters. Remember, we want our distance to be in meters, so we're going to chuck on times 10 to the negative 3, or 0.05, whichever one you prefer. I like to use multipliers just because I'm quirky like that, I guess. The other thing we know is our voltage, which is 10 volts, easy peasy. And then the last thing is what we're actually looking for, right? We're trying to find the magnitude of the electric field. We are trying to find E, that is. Now remember, we've got our two formulas for E. One of them is our electric field is equal to our force divided by our charge, or in other words, force equals charge times electric field. And our other formula is our electric field is equal to voltage divided by our distance between them. And so, just as a general calculation tip as well, it's usually a good idea to write out all of the formulas that use the thing you're looking for, because maybe then you'll be able to figure out, oh, okay, like I know how to find out all of these different things. I know how to calculate these things because in this question we've been given our voltage, we've been given our distance, so we can use this second formula. We can chuck all of our numbers and we can do 10 divided by 5 times 10 to the negative 3, which is a lot of fun. Chuck it into your calculator and you should end up with 2,000. And because we just use this formula, I'm going to say 2 times 10 to the power of 3. We can do volts per meter. However, it is also perfectly correct if you decide to do newtons per coulomb, because they mean exactly the same thing. They are exactly the same units, which is a lot of fun. And hey, if you wanted to do a cheeky maths problem, you could probably play around with why those two units are the same. I think it has something to do with energy, which you might find interesting. But enough with electric fields, right? You've done electric fields before, they're kind of boring. Let's jump into some spicier, newish stuff. Now, you have done an intro to magnetic fields, but that's where we're really going to kick off with some of the new stuff for this module. Now, magnetic fields are also vector fields, in the sense that they point in a particular direction. But unlike electric fields you could just have like a positive charge, and then the electric field just like goes outwards from there. Magnetic fields always have to come in dipoles, which basically means they have to have like a start and an end. They can never really exist just as like a positive side and a negative side. They always need to have a north and a south pole. So as a result, their field lines usually look like these nice little butterfly looking things, where they curve around from the north side to the south side. You can kind of imagine, if you could see inside the magnet itself, you can kind of imagine that the field lines would just sort of continue. And because I'm doing red on red, you can't really see it. But imagine that inside inside the magnet itself, they sort of continue back through from the South Pole to the North Pole, which is how these field lines don't just like exist as like North Poles and South Poles. They always have to go through in this nice complete loop. In Module 7, you'll take a look at Faraday's laws, and the second one basically just says that they always have to come in dipoles. You can't have a magnetic monopole. A fancy way of writing it is this upside down triangle dotted with B is equal to 0. If you're interested in calculus and stuff, you can look up what that is. But aside from that, that's all I'm going to say about that. Now, one quick tangent on a little bit of notation with field lines, because what we're about to dive into is a little bit of three-dimensional field line forces crossover stuff. And because, to be honest, even though you've done like dynamics, you've done like kinematics and all of that stuff, a lot of the stuff you will have encountered so far is only two-dimensional. You haven't encountered a ton of stuff that's dealing with three dimensionals, but in this topic, we are going to be really diving quite deeply into things that might be moving in multiple dimensions where we need all three dimensions. But unfortunately, our paper only, like our nice, neat screen and paper and stuff, only has two dimensions. So as a result, we need something to help us deal with the third dimension. So as a little bit of notation, we can write something moving into the page as a series of crosses, and we can write something that's sort of sticking out of the page or coming back towards us by a series of circles or little dots. So this basically just means that you can kind of imagine, instead of having like a field that's going over to the left, sorry, I say a field going over to the left and then draw one moving to the right, a field moving over to the left, or a field moving over to the right, you can imagine we've got one that's going directly into the page. It's like moving into the screen, whereas here we've got a field that's coming back out of the screen towards us. Now, I like to imagine that the way that I sort of visualize this and remember it in my head is I sort of think of like a bow and arrow. This is a very classic example. Your teachers would probably use the exact same analogy, and the reason is because it's a great analogy. You can imagine like a bow and arrow, right? Like those arrows that you shoot out of a bow. Here's my very dodgy drawing. That's horrific. Let's see. This is why I'm like a physicist and not an artist. This is why I didn't go to art school, guys. That's even worse. I am so. Welcome to Tim's art class. This isn't what you thought you signed up for when you came to my recording. But hey, it is what it is. Okay, imagine it's like an arrow, okay? It's zooming through the air. Don't judge me. It's okay. Um, so imagine we've got this arrow and it's flying through the sky. If this arrow is coming towards you, what you're going to see is that little knob on the end, right? The arrow tip. You're about to die. Um, but that thing coming towards you is a lot like that little dot that's coming towards you if a field is moving out of the page. Whereas if this arrow is moving away from us, what do you see? Well, you see a little fletching at the end. You see those little arrows that whoever those little feathers that like the arrow maker has stuck into the end of the arrow. And that's what I like to remember when you see a field moving away from us. That's what these little X's are. They're the little fletching at the back of the arrow as it's going away from you into the page. Um, so essentially, whenever we have something that's moving into the page, we can represent it with all of these X's, and whenever we have something that's moving out of the page, we can represent it with all of these little dots. Most of the time, 90% of the time, this field is going to be a magnetic field. But the reason I want to bring it up now, and the reason I just want to emphasize the fact that it's just a field, is because occasionally you will actually have like an electric field, or hell, you could even have like a gravitational field that's moving in or out of the page. And so sometimes when you're doing your exam, like you get tricked by thinking, oh, it's an electric field, sorry, it's like a magnetic field, when actually get pranked, it's an electric field and you've just lost a mark. So just keep that in the back of your head. Even though most of the time it's a magnetic field, it doesn't have to be a magnetic field. It can be an electric field as well, which is great. Now, one of the really interesting things about magnetic fields, right, is we've seen anything that has mass will generate a gravitational field. Anything that has charge will generate a electric field. But in order to generate a magnetic field, we need to get the charge moving. So basically, any charge that is moving is going to generate their own magnetic field. Now, I'm pretty sure I'll chat about this. I'm going to chat about this a bit more in just a second. But one of the ways, actually, I will chat about that later. I'll leave that for later. Sorry. Um, and basically, that magnetic field can like interact with external ones to create a force, or can interact. And when I say external one, I mean that could be a magnetic field of another particle. It could be a big external, like huge magnet that you've got. It could be a bar magnet. But just like how when you've got two interacting gravitational fields, that creates a gravitational force, or two interacting electric fields, that creates an electric force. Whenever you've got two interacting magnetic fields, that will also create a magnetic force as well. Now, the formula for our magnetic force is given like this. It's our magnetic force is equal to QVB sine theta. Ignore the sine theta for now, just focus on the QVB, that's the important part, where F is our force, it's measured in newtons. Q is our charge, it's measured in coulombs. V is the velocity of a particle, right? So this is why we actually, like, this sort of emphasizes why we actually need to be moving. Our particle needs to be moving in order to generate a magnetic field, because if it does, and like as a result, if it only experiences a magnetic force when those two fields like interact with each other, you actually need to be moving to experience the magnetic field force. And if you're not moving, you won't experience the magnetic field force. So that's the velocity of our particle measured in meters per second. B is our magnetic field strength. That's probably the only like really new one in this one, is our magnetic field strength. And if you can remember, it is measured in Teslas, which is a fun unit. Now, sine theta is a bit of a funky thing. It basically measures the angle between the magnetic field lines and the direction of your charged particles. So you can imagine if you've got some kind of magnetic field that's moving along like this, and let me change color real quickly. Okay, let me not change color, but imagine you've got some particle that's moving along in this direction. The angle between these two, that little theta here, is going to be the angle in that sine theta. As a result, if you're decently comfortable with your maths and trigonometry, you may notice that sine theta starts at 0 when the angle is 0, sine theta is 0, and then slowly grows up to 1 as the angle increases to 90 degrees. And so as a result, we actually get a maximum force when your magnetic field lines and your charged particle are moving at right angles to each other. If they're perpendicular to each other, if they're moving perpendicularly, you get a maximum force. And if they're moving in the same direction, you actually don't get any force at all, right? Because theta would be equal to 0. It's kind of like if they're moving, well, it is. If they're moving parallel to each other, you get no force. If they're moving perpendicularly to each other, you get a maximum force. Now, the funky thing here is the way that so that's how we calculate the force. But the really interesting thing and the kind of funky new thing with magnetic fields is the way that we figure out the direction of the force. And it's using what we call the right-hand palm rule, or at least what I like to call the right-hand palm rule. Because you may remember from year 11, you learned a little curly rule, which I like to call the grip rule. And don't worry, that rule is also very important, and we'll get back to that later. But for now, forget about it, all right? Imagine you never learned that rule before, except for the fact that it's like a right-hand rule. And basically, the way that we measure, the way that we figure out the direction of this force is if you point your thumb in the direction of the particle's motion, you point the rest of your fingers in the direction of the magnetic field line, you can imagine that you're kind of like a little Jedi kind of thing, and the force is coming directly out of your palm, right? So it's pointing towards like wherever your palm is pointing. Now, one last little side note for that, and this is something that, once again, really, really super important that you get on top of because it's something that a lot of people make mistakes with. But this is only for a positively charged particle. For a negatively charged particle, because it's going to move in the opposite direction to an electric field, sorry, to a positive particle, instead of the charge coming out of your palm, it's going to come out the back of your palm. Basically, it's going to come out the back of your hand, shoot to wherever that is. If you really, really like on top of that, and you feel comfortable with that, you can actually use your left hand instead for negative particles because basically it's going to give you the same thing. Just like if you want to test for yourself, right, you can hold both of your hands in the same position and you'll find that the palm of your left hand points in the same direction as the back of your right hand. But I would encourage you for the most part, just stick to your right hand because you don't want to accidentally like use your left hand when you're doing a positive particle, like whatever. And personally, to be honest, I'm a left-handed person, so I enjoy, not having to put my pen down when I want to do something, right? So I'm just lazy, I guess. I just always use my right-hand rule. So just in summary, right, we can calculate the force using F equals QVB sine theta, which has a maximum when the direction of our particle and the direction of our magnetic field lines are perpendicular to each other. And also, as a result, we will get a force that's pointing out of our palm, wherever our palm is facing. Now, just as a quick practice for everyone who's watching the video, let's actually try using this. So I've got this situation here where I've got an electron. It's moving in a particular direction through a magnetic field. Remember, you can use your right-hand palm rule to figure this out. So your thumb points in the direction of motion of a positive charge. Your fingers point in the direction of the magnetic field lines, and your palm will show the force on a positive particle. So if you want to have a go at this question by yourself, feel free to just pause the video. But aside from that, let's jump into it. So the first thing that I would encourage you to do is actually identify, depending on how comfortable you are with this notation so far, is just identify, is this field going into the page? Is this field coming out of the page, right? So if you remember back to my arrow analogy, what we see here, what we're seeing is the like little feathers on the fletching of the arrow, which means that we're looking on the arrow, looking at the arrow as it's going away from us. So as a result, we can say that in this case, the magnetic field is going into the page. The next thing I can identify, so if you want to sort of keep track of it one by one, you can sort of point your right hand and you can point your fingers moving into the page. The next thing we need to do is identify what is the direction of the particle. Well, our particle is moving over towards the right, so you can flip your hand around and you can say, okay, my thumb is now pointing in that right-hand direction. Lastly, we then just need to figure out, okay, we've got the right direction of our magnetic field lines, we have the right direction of our motion. All we need to do is figure out the direction of the force as a result. And our palm is facing upwards. So we would think, okay, yeah, the force is pointing upwards. But you may remember from a couple of minutes ago when I said that's only true for a positive particle, which means in this case, because we've got an electron and an electron is negative, it's going to be going in the opposite direction, right? So instead of having a force going upwards, our force must be coming out the bottom of our palm, pointing downwards. And so as a result, we can say that our particle, our electron, is going to experience a force pointing down the page. So the sort of formal technical language that we use is we say that it's coming down the plane, down the page, sorry. Another way you could put it is down the plane if you want to be like really super fancy. But those are the two main descriptions I would probably, those are the two main descriptions I would probably use to describe what's going on here. So yeah, just in quick recap, right? We've got our magnetic field going into the page. You can use your thumb to point in the direction the particle is moving. And then the force, because it's a negative particle, is coming out the back of your palm, and so that tells you which direction that force is going to be moving. Okay, now that's out of the way, let's try and have a little bit of a practice of actually calculating that magnetic force strength, right? Not just using our right-hand palm rule, but also trying to use that formula that we learned as well. So the formula, if you remember, says F is equal to Q times V times B sine theta. Now in this case, and the reason when I wrote this formula out for the first time, I was like, oh, don't worry about the sine theta, is because probably in like 80% of cases, you can just assume that your particle and your stuff are moving perpendicular to each other, because in most cases, they honestly are. Like it's not super common that they're not moving perpendicularly. That's not to say that it never happens. Like if you have a question that's trying to trick you, sometimes they'll be not perpendicular. Keep an eye on it, but for the most part, you don't have to worry about it, is what I would say. Now in this case, because I forgot to when I wrote the question, we can just assume that they're moving perpendicular, and so as a result, we can get rid of that sine theta. Just once again, if you're confused about why we can do that, perpendicular means 90 degrees, sine of 90 is equal to 1, so it's basically just doing like Q times V times B times 1, which means we can get rid of the sine theta, just so we don't have to write as much and it's not quite as gross, and I don't know, it's personal preference, okay. Aside from that, now that we know the formula, we've got the formula down. The reason I wrote that is because we're trying to calculate the magnetic field force. So let's chuck that down. Aside from that, let's chuck down all of the other numbers that we know. So we know that the magnetic field is 10 Teslas. So we could write B is equal to 10. We're also told the velocity of the proton, which is the velocity is equal to 1 times 10 to the power of 6. Which just leaves us with the charge of the proton. Now, you don't remember from year 11, a proton has the same charge as an electron. It's just that instead of the electron being negative, the proton is positive. So it's sort of like a positive version of whatever the charge of the electron is. And if you don't remember that, no worries, just flick over to our trusty formula sheet, scroll up to the data section, and it is in fact the top entry here. It's the charge on the electron as negative 1.602 times 10 to the negative 19 coulombs. But of course, because this is a proton, it's positive, so it's going to be positive 1.602 times 10 to the negative 19 coulombs. And yes, sorry, I should have included my units beforehand. Our magnetic field strength is 10 Teslas. Our velocity is 1 times 10 to the 6 meters per second. And we can just chuck all of those numbers in. So let's say our magnetic field force is going to be 1.602 times 10 to the negative 19 times our velocity, which is 1 times 10 to the 6, times our magnetic field strength, which is 10 Teslas. Chuck all of that in, and you get 1.602 times 10 to the negative 19 times 1 times 10 to the 6 times our 10 Teslas, which if you chuck that into your calculator, you end up with 1.602 times 10 to the negative 12, and that's in newtons. Now, if we were given like a diagram, we could figure out what the direction is, But in general, if we haven't like this case, you probably don't need to chuck a direction in. But remember, because this is a positive particle, if you were to hypothetically, you know what? I'm talking about it. Let me just quickly draw up an example, all right? Let's say, actually, we've kind of done that one already. Let me, if you want to skip ahead like 5 seconds until I've actually drawn the question out, that's fine as well. I'm probably not going to add too much like crazy interesting insight, but yeah, let's say we've got a field that is made up of a whole bunch of little dots. And our proton, to spice things up, let's have our proton, lovely particle moving down the page like that. Which direction is our magnetic field force going to be going? Now, I'm sorry because I just wrote that question just then. It's not going to be in the little Slido thing down below. However, this question would have. And sorry, I'm not sure if I mentioned it before, but basically, if you ever see a star in the side of the question, that means that there should be an associated Slido question. So even if I don't explicitly mention it, when you see the star, you can be like, let me go search. Let me go find this question down below so I can have a go at it myself. Anyway, now that I've got the question up, let's have a go at using our right-hand rule. So once again, we need to figure out, first of all, which direction is that magnetic field moving in? Because we've got all the dots. Remember, the arrow is coming towards us, which means the magnetic field is coming out of the page, which means you point your fingers back towards yourself. The next thing we need to do is figure out which direction the particle's moving in. It's moving downwards, which means point your thumb pointing downwards. And so now you've kind of got this weird, like, anyway, you've got this weird, like, hand arrangement. But the important thing is you can now see your palm is facing over towards the left. And because it's a positive particle, it means we can actually use our palm for the first time, which means our force is moving over towards the left. Is the direction that it is going to be pointing. But that's like one of the funny things with physics is you'll go into your physics HSC and there'll just be a point where like everyone's playing around with their hands, like it's the secret physics gang signs, right? Is all of the right hand rules that we have to play with, which is quite a bit of fun. But yeah, so our magnetic field force 1.602 times 10 to the negative 12 newtons, and it's pointing over towards the left in this specific scenario that I dreamt up. All right. Hope that is all lovely. Now, I've already had a little bit of a rant here about the sine theta, and the reason I'm not a massive fan of the sine thetas. I just want to preface all of this by this is very much my personal preference, and so if it works for you, it works for you. If it doesn't work for you, just completely ignore this, skip across to the next slide. But personally, I don't like all of the sine thetas and cos thetas, right? If you take a look at your formula sheet, if you take a look down here, there are so many cos and sine thetas, all right? I say that as not being able to find any, right? 1, 2, 3, 4, there's a cos squared, there's a lot of thetas and cos thetas and sine thetas, and there's another one there, and there should actually also be a cos theta at the end here. Sorry for this dodgy formula sheet. This is not the proper formula sheet. I'm sorry about that. Let me, just because I'm going to get annoyed, let's look up physics formula sheet. This is literally what I mean when I say look up the physics formula sheet. Let's find the actual physics formula sheet. I like, this is the one produced by NASA as well. NASA, why are you like baiting us with this wrong formula sheet? Don't know what this is, but let me chuck in HSC to do this. Here we go. This looks better. And the Wi-Fi is just struggling. No, why is this dodgy? Okay, I'm sorry. We're gonna stick with this dodgy one for now because I can't find a better one. But your actual formula sheet, just in case you don't know what I'm looking for, it should be structured in different sections. It should have like the gravity section should have then below like the waves and stuff section, and then the electromagnetism section, and then down the bottom is the like quantum and special relativity and all that stuff, which is a lot of fun. Anyway, back to my aggressive rant on sine theta and cos theta. Basically, they're in all of the different formulas, and they all mean different things. Like sometimes they're talking about the formula, like the angle between two elements. Sometimes they're talking about the angle between an element and a normal. Like it just gets confusing. So if instead, the way that I would encourage you to do it is just try and do it through intuition. So if you remember that your force, your magnetic field force, reaches a maximum when your two things are perpendicular and reaches a minimum when your two things are parallel. You can just sort of remember that like that's the angle that we're dealing with, which is that the angle is between the like you have your maximum there, you have your minimum there. And if you then remember that sine reaches a maximum at 1 at 90 degrees, and sine reaches a minimum when they're parallel, i.e. when we have 0 degrees, whereas cos has a maximum at 0 degrees and a minimum at 90 degrees. If you're ever sort of struggling to remember whether in a particular situation to use sine or cos and what angle to use, instead just kind of, I would encourage you to just remember, like, where do we get a maximum, where do we get a minimum, and that should direct you as to whether to use sine, whether to use cos, whether to use like what angle or whatever. If that all went over your head, don't worry, but this is just me saying, if you like sine and cos and you feel comfortable using them, this is your okay. This is your sign to just forget about them. No pun intended. If that all went over your head, just ignore it and try and memorize which sine and cos. That's fine. It's just, this is personal preference. I don't like remembering what sine and cos are. And so just like when we encounter more sines and coses later on in today's lecture, that's why I'm gonna hate them, which should be a lot of fun. Um, okay, that pretty much brings us to the end of electric and magnetic fields. Just as a quick side note on how this lecture is kind of working, is I'm not going in every like single topic in a whole bunch of detail, just because like I probably wouldn't have time, and this recording would be hours and hours and hours if I went through every single topic. So I'm just sort of trying to give you a taste of like the really important topics and give you a little bit of practice of the fundamentals. But just in terms of other things that you'll look at quickly in electric and magnetic fields, the big thing that you'll look at is the comparison between electric fields and gravitational fields, and basically comparing the two. I've already done a little bit of that, but in terms of difficult questions, the reason that that can get quite difficult is the fact that you can have, just like how gravitational fields allow you to do projectile motion, electric fields can also give you projectile motion as well. And so if you see a question in an exam or something that has electric fields giving you projectile motion, don't stress. The only thing you need to do is you calculate the force, and then you can use Newton's second law, F equals ma, to calculate the acceleration. And then once you've got the acceleration, it's just you do the question as normal. Which is a lot of fun. One other last side note is that if you are particularly very clever and you've picked up on stuff nice and quickly, you may remember that you may have noticed that the force is always acting perpendicularly to the other two like objects, right? It's always acting perpendicularly to the magnetic field lines, and it's always acting perpendicularly to the direction of motion. It doesn't always mean necessarily that the magnetic field lines and the motion themselves are perpendicular to each other, but it always means that the force is going to act perpendicular to those two in whichever direction that they are pointing. If you're particularly eagle-eyed or eagle-brained, or I don't know, you picked up on it, this means that we've got a force that is always acting perpendicular to the direction of motion, which to those of you who have done Module 5 will ring some bells as the exact recipe required to give us circular motion. And as a result, we can say that our magnetic fields will actually give us circular motion. If you have a constant magnetic field and you've got a particle that's chilling in it and is moving around, it's going to move in a nice neat circle. And that's something that's important. It comes up quite a bit in Module 8, but it's also a nice link between Module 5 and Module 6. It shows us that, you know, these things do actually come together a little bit. NASA isn't just messing around, even though sometimes it might feel like it. So with that out of the way, let's take a look at our next topic, which is the motor effect. Sorry, hydrate, dihydrate. We've looked so far at our electric fields, we've looked at our magnetic fields, and now we're going to take a look at, well, how can you actually maybe start to use them in some real applications. Now, the motor effect is defined as a current carrying conductor the fact that a current carrying conductor in a magnetic field experiences a force. I'll give you a much more concrete definition in just a second, but basically what this tells us is that if you have some current carrying conductor, i.e. like a wire or a piece of metal, basically if you have some kind of current flowing and you chuck that inside of a magnetic field, it's going to experience a force. Now, I've got a couple of hot tips that I want to include throughout my lecture, and my first one, is just the fact that whenever you're writing an extended response or even just like a written response in general, I really, really highly encourage you to use jargon in your writing. So jargon basically just is referring to those kind of technical words, those little spicy words you can include in a response, that just really show the reader that you understand what you're talking about, that you really, really understand the things that you're discussing. And there's a couple of big benefits to using them. Number one is that they show that you've studied, they show that you understand them, particularly if you're using, and side note, you should always really only use your jargon and your keywords in the right situation, i.e. like don't be talking about the motor effect when you're dealing with like projectile motion or something like that. Um, but if you drop them in at exactly the right time, they will just wow your like reader, wow your marker. They'll be like, wow, this person, this student just knows absolutely everything. They're so smart. Let's give them a band six right on the spot, which we love. We stand that. The other reason is that it will really help to condense your writing a lot, because I know something that a lot of physics students struggle with is like you read a question and you're like, I know how to answer this, like I know exactly how I'm supposed to do this, but then like there's like three lines of writing like that the question has given you, and you just write for an entire page. The reason a lot of times you're doing that is because you're trying to explain things that like other people have come up with words for, and those words are our pieces of jargon. So for example, if you're trying to refer to the force that a current carrying conductor experiences, instead of saying, this wire will experience a force, you can just refer to the motor effect, which is what we're talking about here. Um, so why does this happen? Now, I want to preface this by this is a slightly dodgy definition, so it's not 100% accurate in every single way, but it gives you a good idea as to like why it happens in the first place. Basically, if we've got our station, we've already seen how a stationary electron experiences an electric field, and a moving electron experiences or has both an electric field but also produces a magnetic field as well. Therefore, all charges are going to be surrounded by a magnetic field. Therefore, a current, which you may remember is just a whole bunch of charged particles moving together, is also going to be surrounded by a magnetic field. Now, you learned this in year 11. You may remember that, like, if you have some current carrying conductor, you can figure out the direction of the magnetic field around it using the right-hand grip rule. So just to be very clear, this is different to the right-hand palm rule, which we experienced before. This is the right-hand grip rule, where basically you can point your thumb in the direction of the current, and your fingers will then point in the direction of the magnetic field that's surrounding the current. So in this case, let me draw a slightly clearer one. If we've got a current that is pointing downwards, you can stick your fingers around, like you can imagine that you're kind of gripping or grabbing onto the coil or the piece of wire, and that will indicate the direction of the magnetic field that's going around it for you, which is really, really sweet. And in fact, so let me try and draw that. It's like moving, that's bad, a bad drawing. It's moving around like that. Um, I'm really not great at drawing, hey. Anyway, yeah. We can also represent that instead, now that you've seen our lovely notation for going in on one side and out on, like, for going in and out. You may notice that, like, if you imagine you took like a clean swipe of my hand, on one side of my hand the field is going into the page, whereas on the other side of my hand the field is coming out of the page. And we can actually draw that down here. We can draw a whole bunch of X's down along here to represent how it's going into the page on one side, and a whole bunch of dots to represent how it's coming out of the page on the other side. Okay, that was a lot. Let me just quickly recap. So we know that a charge, when it starts moving, produces a magnetic field. A current is just made up of a whole bunch of charges, and so as a result, it produces a magnetic field around it, and we can figure out what the direction of that magnetic field is using the right-hand grip rule. Just in general, I'll try and explain this a little bit more later on, but because we've now seen these two different right-hand rules, I would encourage you to try and use this rule more. Like the palm rule that we saw beforehand is pretty much exclusively just used for the case where you have either the motor effect by itself, which is the case we're about to see coming up, or you have a charged particle experiencing a force. Pretty much everything else, when it actually, okay, whenever we're dealing with a force, we use the right-hand palm rule. Whenever we're dealing with like the relationship between the direction of a current and a magnetic field, we use the right-hand grip rule. is probably the way I'll try and explain it the best, and I'll try and like rag this up a lot more as we go through the rest of the lecture. But I just know that that's something that a lot of students struggle with is like the now that we've got these two different right hand grip rules, where do we use one? Where do we use the other? Palm rule is for force. I don't know, maybe like it looks like you're trying to high five someone, and when you high five someone, it applies a force on them. That was horrific. I'm so sorry, but that was me trying on the fly. Okay. Um, Whereas our grip rule, right, is like when you're trying to find the relationship between current and magnetic field, and when you grip someone's hand, you're building a relationship in some way, shape, or form. Uh, that was a stretch. I'm sorry. Please forgive me. Let's move on. So the magnetic field produced by currents can interact with another external magnetic field, and just like when we had our magnetic fields interacting beforehand, we experience a force once again. Now, this is basically the same magnetic field force. It's just that instead of being the magnetic field being applied to a single particle, it's the magnetic field being applied to a whole bunch of particles at the same time in the form of a current. Now, if you're particularly cheeky, you will have noticed that this topic is called the motor effect. We won't actually talk about motors until the very last topic, but the reason it's called the motor effect is because basically what you've got here is you've got a force being applied to a wire, i.e. a force rather than just being applied to a single particle, a force is being applied to a whole thing at the same time. So the way you figure out the direction of this force is through the right-hand palm rule. It basically works exactly the same way as our right hand. It works the same way as our right-hand rule for our forces on single particles. The only difference is instead of having the direction of particle, it's the direction of the current, which is basically the same thing, right? Because a current is just a whole bunch of particles moving in one direction. So just to quickly recap, you can figure out the direction of the motor effect force by pointing your fingers in the direction of the magnetic field lines and your thumb in the direction of the current, and then the force is moving out of your palm. Yeah, that's pretty much all there is to this. Just a quick reminder, your current is always pointing in the opposite direction as the flow of electrons. So because we imagine current as being movement of positive particles, that's always moving in the opposite direction as the flow of negative particles, which is a whole lot of fun. Now, the magnitude of the force, well, it's dependent on the size of the magnetic field, it's dependent on the size of the conductor, and it's the size, i.e. like the size of the wire, and it's also dependent on the amount of the conductor that's actually exposed to the magnetic field, and the angle as well. Which means that our formula actually takes a very similar form to our charged particle formula, which is our F equals QVB sine theta. Like there's a lot of similarities between the two. Now there are reasons for that because basically the number of charged particles in a particular region you can kind of convert between the two, and it's a lot of fun. And it really is essentially the same formula. It's just for two different situations. We use this formula if we're trying to use a single particle. That's where we use this one, whereas this one we use when we have some kind of conductor, some kind of wire. Is where we use that. I can't spell conductor. One of the fun things about me is I find when I'm talking and I'm trying to write, my spelling just falls off a cliff, which is lots of fun. So just quickly, our force is measured in newtons, our length is measured in meters. This is the amount of stuff that's in the magnetic field. Sorry, our current is measured in amps, and our magnetic field, once again, is measured in teslas. I realized I never gave you a quick little like recap, but just in case you forgot, current is just the motion of little particles inside our wire, and it's measured in amps. It's cool, which is lots of fun. So let's actually jump into a practice of trying to use this formula. Remember, as always, if you want to give it a crack yourself, you can go down into the Slido down below, and please do give it your best shot. It should be fun. So in this question, we're going to calculate the magnitude of the force on a 2-meter long power cable, which is carrying 10 amps of current, if it is laying at an angle of 30 degrees to a 2 millitesla magnetic field generated by an MRI machine. So remember, we're going to be using our formula. Force is equal to length times current times magnetic field times sine of theta. For this case, I reckon it's probably a good idea to draw out a cheeky little diagram. So we can say here is our magnetic field. It's our 2 millitesla magnetic field. Wow, so crazy. Wow, Tim, you're such a good drawer. That's crazy. Thank you guys. So wonderful. See, I'm going crazy by not having you guys to speak too loud. Okay, I'm sorry. Okay, so here is our wire. Let me actually try and grab a different color this time so I'm not just drawing um full red on red. Here is our beautiful wire. It's laying, this is a pretty dodgy 30 degrees, but here is our angle of 30 degrees. And I know I realized I didn't mention it when I brought up the formula, but basically the sine theta works in the exact same way as it did for the single individual particles like before, right? It reaches a maximum when our y is acting perpendicularly, and it reaches a minimum when it's acting in parallel. Um, Now, just the reason I think that this diagram is useful is because it shows to us, oh, in this case, as much as Tim may like to pretend that the angle doesn't exist, in this case, it is actually going to be important. So let's quickly write down all of the numbers we know. We know that our force is measured in newtons, and that's actually what we're looking for. Sorry, we're trying to calculate the magnitude of the force. We know that the length of the power cable is 2 meters long, so we could write that down as 2 meters. We know that it's carrying 10 amps of current. It's a very powerful power cable. To be fair, it's not that crazy. Sorry, it is semi-realistic. It is crazy current, but like it's not wild. Our magnetic field is given to us as 2 millitesla. Remember the multiplier milli is times 10 to the negative 3. And finally, we're told that our angle is 30 degrees, so we could write this down as theta equals 30 degrees. And so now we've got all these numbers, we know what our formula is, we can kind of play match, join the dots, and just sub all of our numbers in. We can check off, yes, I know what every single thing means, let's just chuck them in the formula. So we can say our force is equal to our length, which is 2 meters, times our current, which is 10 meters, times our magnetic field strength, which is 2 times 10 to the negative 3, times sine of the angle, which is 30 degrees. You can chuck all of that into your calculator. You get 2 times 10 times 2 times 10 to the negative 3 times sine of 30, which if you do all of that, you end up with 0.02. Remember, it's a force, so it's measured in newtons. We could also write this as 20 millinewtons as well. And that is going to be our force. And you know what? Just to practice some things, let's say hypothetically the direction of our current is down there. Our current is flowing in that direction. If you want to, I know this isn't going to be on the Slido down below, but if you want to just quickly practice which direction is that force going to be acting in, well, if you do that, you should be able to figure out, okay, our current is moving downwards, so sort of line your thumb up a little bit. This one's going to be slightly tricky with the direction of the current. You can put your fingers in the direction of the magnetic field, and all of a sudden I'm realizing I've kind of made myself, my thumb doesn't go that far, right? My thumb kind of sucks. But if I can kind of imagine what would happen if I could like dislocate my thumb or whatever to get it round. Kind of. It's a bit of a struggle, right? But anyway, my fingers are pointing like that, my thumb's kind of pointing around like that, and as a result, my palm is pointing towards myself, so I can say that the force is going to be coming out of the page, right? The force is pointing back towards me, which is a lot of fun. If you could actually do that, chuck it in like a Q&A something, because like, man, I would be very impressed if you can move your thumb that far. My thumb is hurting. I regret doing that, okay? But yes, that is our lovely drawing that I did before. That is our stuff. Cool. Now let's have a cheeky bit of practice with a past HSC question. This is one that I got from the 2012 HSC. Just to show you, this is actually the kinds of things that you might be dealing with in your HSC proper. So in this situation, and once again, this is an HSC question. We've just done a practice. There's not a ton of difference between what we've done in this question and what we've done in the last one. So I really do encourage you, if you want to give this one a bit of a practice by yourself, pause the video and go down to the Slido and give it a crack by yourself. Hey, doing an HSC question in January, that is what I love to see, all right? You're really getting on top of it. But yeah, let's jump into this one. So a current carrying conductor, or current carrying wire, sorry, passes through a region of uniform magnetic field with a magnitude of 0.05 teslas, and as a result, it experiences a force with a magnitude of 0.03 newtons. Our question is, what is the current going to be? Well, it is slightly trickier than the one that we've just done, but once again, we can kind of use our same technique. We don't have to draw a diagram because they've already given us a diagram, which is very much thank you, Nessa, stand this question. But let's quickly write down all of the information that we've been given. So we can say that our force is equal to 0.03 newtons. So we can chuck down force is 0.03. Um, and because this force that it's experiencing, remember, is the motor effect, we can use our motor effect formula, or force on conducting current carrying conductor, to just quickly jot down, okay, we know that this force of 0.03 is equal to the length of the conductor times the current passing through the conductor times, sorry, B, I forgot B, shouldn't forget B, that's uh, unfortunate. Must remember that B is something that exists. We need justice for B. Times our magnetic field times sine of theta. Now, because we're looking for our current, this is the thing we're looking for, we can quickly rearrange the formula, right? We can divide across by L, we can divide by B, we can divide by sine theta to get that our current is equal to the force divided by the length times the magnetic field times sine of theta. You can do this in any order that you like as well. I just prefer to rearrange my formula and then sub in numbers rather than sub in numbers and then rearrange my formula. But now that we have rearranged the formula, we can start subbing in some of our, well, we can write down the rest of our numbers and then we can start subbing some of them in, right? So our checklist is we need the force, we need the length, we need the magnetic field, and we need theta. So we've got force, bing, bing, bing. What other numbers do we have? We've got our magnetic field strength, so 0.05 teslas. So that gives us B, sorry, I'll write down B is equal to that. Which leaves us with our length and our value of theta. Let's start off with our length. Now, we aren't given any other numbers in our question, which means a good idea is probably going to be turning to our diagram and seeing, okay, how can we figure out what our length is based off the diagram? And if you look on our diagram, we're actually given a couple more numbers. We're given an angle of 30 degrees and we're given a length over here of 0.2 meters. Now, our length, remember, is the length of the wire that lies inside the magnetic field, which is basically going to be this side length over here, this whole diagonal that passes through the magnetic field, which, looking at it, we can actually kind of interpret as just being the hypotenuse of this triangle. We can kind of draw a little triangle where this side is 0.2, this little angle is 30 degrees, and we are looking for the length of this third angle over here. So we can do this using a little bit of cheeky trigonometry. Even though they haven't drawn that out as a right angle, we can probably assume just looking at it, it's basically a right angle. And so we can figure out this third side length using our lovely trigonometry. So because we are interested in the hypotenuse and we know what the opposite angle is, probably what we should use is our sine. So we can say sine of 30 is equal to our opposite side divided by our hypotenuse. Our opposite side is what we know, which is 0.2 divided by our hypotenuse, which I've kind of, okay, I've written it as the question mark. Maybe that's not the most clear pronumeral to use, but now that we've got this formula, we can rearrange. Let me write it slightly clearer up here. So we can say sine of 30 is equal to 0.2 divided by our question mark. Rearranging it, we then get that our question mark is equal to 0.2 divided by sine of 30, which if you chuck that into your calculator, you end up with a value of 0.4, which is quite nice. It's quite a nice, neat answer. But yeah, that is our length. We now know that our length is equal to 0.4. So checking that off our list, we've got our force, we've got our B, we've got our length, which means all that's left is our value of theta. If you want, quickly pause the video and try and figure out what that value of theta is going to be. Because it's a little bit of a tricky one. But if you've had a little bit of a pause, had a little bit of a think, had a bit of a look at the diagram, right? I have low-key, sorry, I have kind of drawn over the diagram here. So let me get rid of that so you can see it slightly clearer. But up the top here, we're told that the direction of the current is down here. Current's pointing downwards. But the direction of the magnetic field is actually into the page, right? So if you try and like make that on your hand, right, your thumb is pointing that kind of like downwards diagonal direction, but the rest of your fingers, because we've got all those X's, right, the arrows moving away from us, the rest of your fingers should point into the page. And what you notice is that even though it's kind of tricky to draw here, the magnetic field is moving away into the page, that's still perpendicular. They're still at a right angle to each other. So even though we're given this cheeky little 30 degrees over here, it's a bit of a red herring. It's a bit of a trick to try and trip you up. Instead, our theta is actually equal to 90 degrees. That's actually what we're dealing with over here. Still the classic 90 degrees. And so as a result, remember, sine of 90 is just equal to 1. And so we can just get rid of that. We can ignore it. We don't have to worry about it anymore. So our force is equal to 0.03 divided by our length, which is 0.4, times our magnetic field, which is 0.05. Chuck all of that onto your calculator, 0.03, sorry, I just typed 0.3 divided by 0.4 times 0.05, which if you put all of that in, you end up with a current of 1.5 amps. And so that is the direction of, sorry, that is the value of our current. If you want to be super specific, you can say it's moving on that diagonal. But I mean, we were given that in the question. So to be honest, I don't think it's like one of the most important details you need to include. All right. Hopefully that made a little bit of sense. Let's move on to the next hot tip, which is that if we have a question just like that one where there was quite a bit of work going on, right? Like we needed to rearrange the equation, then we had to like do a little bit of trigonometry to find out what one of our values was, and then we had to figure out like, hey, what's actually happening here? So I really encourage you in like more complex questions like the one that we've just done there. It's often really valuable to bring along a highlighter and highlight as you're reading through the question. You can highlight all of the different parts of the question, all of the different numbers that you're given, maybe the directive term, what you're trying to find. You can highlight all of the important things, and that means that like you don't like forget that they're there, because I find that one of the biggest struggles of physics students is you just forget like what you've used and what you haven't used, like what numbers you've actually got available to you. Like in the last question, we may have struggled because we may have just forgotten that these things were available to us. We may have just forgotten that the diagram existed. And if we did that, trying to find the length would be basically impossible because we don't have the things that we needed to figure out what the length was. Whereas because we did know what they were, like it was all fine. We did know what it was. Okay, so just like we can have some external magnetic field applying a force onto a wire, if we have two wires that are both producing magnetic fields, we can have some like degree of interaction between the two magnetic fields. And this is what we call the force, or the interaction between two parallel, or not necessarily parallel, but current carrying conductors. So essentially what you've got going on in this situation is rather than like one wire and an external magnetic field or something, you've got a wire and then another wire next to it. And because these two wires are both producing magnetic fields, their magnetic fields will sort of interact with each other and cause some sort of force between themselves. Now, the magnitude of the force per unit length between the two parallel wires is given by this formula here, where it's the force divided by the length is equal to this funny little guy, which is called the mu, divided by 2 pi times our current 1 times our current 2 times divided by our radius. Just as a quick side note, as always, this formula is on your formula sheet. Don't worry, I will be very direct and very obvious if you ever encounter a formula that is not on your formula sheet. But just to quickly break it down a little bit, our force is the force that we're very nice and familiar with, which is our force measured in newtons. Our length is the length of the two wires, right? So this is if we've got two really, really long wires, it's however long they are. If it's the length of two really short wires, it's however long they are. You might be wondering why we write the wires and like why we write it as force divided by length rather than just force. And the reason for that is because the length of these wires could technically be like really long. Like imagine like we're dealing with power wires or something like that, like the power grid system, those wire overhead wires that you might see that go like along your street, but then also those massive wires that literally go cross country. Those wires run parallel to each other for a very, very, very long time. And so as a result, your length would be massive. So if you did force is equal to mu zero blah 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 times length, you would up with an absolutely huge force, right? But that's not particularly relevant because your wires is so long, and so as a result, like the force like between 2 points on the wire may not actually be massive, even though the force itself is absolutely huge. So instead, what we do, rather than looking at the force in its entirety, is we just look at the force over a little tiny section of wire, which we call the force per unit length. So anyway, yeah, the force is force. L is the length of our wire that we're trying to analyze. Mu naught is what we call the magnetic permeability constant. It's equal to a 4 pi times 10 to the negative 7. Don't worry really what it is, what it actually means. It's kind of like how easily magnetic field lines are able to propagate. Now you're given it on your formula sheet as yeah, you're given it. Are you given it on your formula? You are given it on your normal formula sheet, just not this cooked version that I've managed to find. I'm so sorry about that, guys. Um, yeah, it's equal to 4 pi times 10 to the negative 7. However, I suppose what this formula sheet has is it's instead got this whole thing, which is mu naught on 2 pi, which we've got written as 2 times 10 to the negative 7, which is what you get if you divide 4 pi times 10 to the negative 7 by 2 pi. You end up with just 2 times 10 to the negative 7 instead. So it ultimately means the same thing. So this whole thing, when you combine it together, just gives you 2 times 10 to the negative 7. Then your I1 and your I2 are just the currents that are passing through your conductor. So it doesn't matter which order you do it in. One of them can just be called I1, one of them can just be called I2, and R is the distance between your wires. Sometimes on some formulas it might be written as D. But yeah, it's just how far your two wires are apart from each other, because once again, like if you bring them further and further away from each other, they aren't going to be experiencing as much like of a force compared to each other, which is how it works. Now, one of the weird things that happens with wires is our parallel wires is if our like normally what we experience is that if two things are like opposite to each other, they're going to attract, whereas if two things are the same, they're going to repel each other. But this is the one case where this is not true, right? So if we have two wires that are pointing in the same direction, i.e., if we have two currents moving in the same direction, they're actually going to attract each other. Whereas if we have two wires that are moving in opposite directions, they are actually going to repel each other. Now, that might seem really counterintuitive to you, but the reason it happens is actually because of the opposites attracting, but not because of the wires, it's because of the magnetic fields that our two things are forming. So if you imagine, let me see, let's flick back. I don't have a nice slide. Let's just do it here. So imagine you've got two wires that both are moving in the same direction. You can use your right-hand grip rule to figure out what direction the magnetic field generated by these two wires is going to be. So if we do it on the left-hand side, we can see that on the left hand of the left-hand side, it's kind of coming out of the page is the magnetic field, whereas on the other side, it's kind of going back into the page. We've got all of these crosses over here. And if you do the same thing on this wire over here, you can see the exact same thing is happening, right? Like on the right-hand side of our curl, sorry, and just, I don't think I said it, but just remember, because it's a wire, we use the grip rule to figure out we're looking at the relationship right between a current and a magnetic field. So we use the grip rule. So once again, it's coming out of the page on the left-hand side and it's going back into the page on the right-hand side. And then you might notice, oh, look at this space in the middle. We've got, it's going in on one side and out on the other. That means those magnetic fields are going to be opposite to each other. And guess what? Those magnetic fields are going to attract each other, which is why when our currents are moving in the same direction, we actually get this force of attraction. Whereas when you've got these currents that are moving in opposite directions, right? Let me do this again. We've got one wire that's moving up, we've got one wire that's moving down. Use your right-hand grip rule. On the one side, it's coming out of the page over here. On the other side, it's moving into the page over here. Down here, it's moving downwards, so it's coming, then because the current is moving downwards over here, you can point your thumb down. It's moving into the page over here and it's coming out of the page over here. Look at how these magnetic fields are going to interact with each other. Ba-bow. They're both moving out of the page coming back towards us, and so as a result they're moving in the same direction, and they don't like that. And so as a result they are going to repel each other. So if you didn't take away any of that, the key takeaway here is that if you've got these two currents flowing in the same direction, you get a force of attraction, whereas if you've got two currents moving in opposite directions, you get a force of repulsion. So if your two currents are flowing in the same direction, the two wires will attract each other, whereas if they're moving in opposite directions, they will repel each other, which is a lot of fun. So with that all out of the way, let's have a go at a little bit of cheeky practice. And as always, if you want to have a go at this question by yourself, you can feel free to do it in the Slido down below. But if not, let's jump into it. So 3 parallel wires, X, Y, and Z, all of length 1 meter, all carry electric currents. A force of attraction is produced between X and Y. There is zero net force on Y. Our question is, what is the magnitude and direction of the current in the position X? Okay, let's dig into this a little bit. There's quite a bit of stuff going on. First of all, let's kind of write down all of the information that we have been told. We know that our length is equal to 1 meter, and that's true for all of them, right? We've got our length is equal to 1 meter, and that's, I suppose the reason that's so nice is it means that in our formula, F is equal to mu0 on 2 pi times I1 times I2 all on R. We don't really have to worry about the like divided by L section because our L is just equal to 1. So we're basically just doing divided by 1, so we can just get rid of that. So now that that's out of the way, we don't have to worry about our length anymore. It essentially just gives us a bit of a nicer formula. Now, we're told that we have a force of attraction between Y and Z. Basically, that means that there's some kind of force that is pulling Z back down. And sorry, there's no other numbers, like there's no really isn't any other numbers in the question. Like there's some numbers on the diagram, and I promise we will get to them when we get to them. But because there's no other numbers in the question, we can kind of just move on to start digging into what other things we are told in the question, right? So we know that there's a force of attraction between Y and Z, which means that there must be something pulling Y down. Now, if you remember back to a couple of slides ago, I said that the force of attraction will occur whenever we have two currents moving in the exact same direction, which means that Z needs to be needs to have a current that is flowing in this direction, which is useful, but we're not really looking for the direction of current Z. We're looking for the direction of the current in X. However, intuitively, we can think about the fact that there's no net force acting on Y, which basically means that if there's some force that's pulling Y down towards Z, there must be an equal and opposite force pulling it back up towards X. Just to go over that again, we're told that there's zero net force on Y. Basically, Y is chilling by itself. There's nothing that's sort of affecting it. But we know that there's a force that's pulling it down towards Z, which means that there needs to be an equal and opposite force pulling it back up towards X, which would be, if you look at this, this is going to have to be an attractive force acting between Y and X, which means that in order to get that attractive force, we need to have X and Y moving in the exact same direction. So essentially, we need to have the current that is flowing through X, we need it to be pointing in the same direction as Y, which means we can answer half of our question just off the bat as saying, we can say the direction of that current is moving over towards the right. So we could say direction is over to the right. Let's make a jot note of that because now I guess we need to get into some of the slightly spicier stuff, which is we need to actually calculate the force between, we need to figure out what the magnitude of the current in X is going to be. Now to do that, we can use the exact same process, which is that we said the force acting on y due to z is going to be equal and opposite to the force acting on y due to x. So we could kind of write that as saying the force due to x has to be equal to the force due to z. Now we know what the current in x and y are, so now let's actually start writing down some of our other pieces of information. We know that the current in y is equal to 20 amps. We also know that the current in z is equal to 20 amps. We know that mu naught on 2 pi is equal to 2 times 10 to the negative 7. You can also just write that as mu naught is equal to 4 pi times 10 to the negative 7. It's up to you. And we also know that the distance between y and z, which is our radius, remember, is equal to 30 centimeters. Now, our radius is measured in meters, which means we need to convert this into meters, and so that's going to be 0.3. So that's our force due to z. So quickly writing out the formula, we can say that the formula of the force due to z is going to be mu naught on 2 pi, all times our I of y times our I of z, all divided by the distance between them. And look at that. If you go through, you can actually check off all of these numbers. We know what all of these numbers are. So you can start slapping some of these numbers in. We've got 2 times 10 to the negative 7 times our current, sorry, that's our mu naught on 2 pi. Our Iy is equal to 20 times our Iz, which is also equal to 20 divided by our radius, which is 0.3. Chuck all of this in, you get 2 times 10 to the negative 7 times 20, all divided by 0.3, which is equal to 2.67 times 10 to the negative 4 newtons. Okay, done quite a bit of calculating, but unfortunately, this is only half of the trek. All right, we haven't quite made it all of the way to the other side. We still have a little bit of work that we need to do. So save that number on your calculator. If you just quick side note for calculator techniques, if you're not sure how to save that on your calculator, you can use the shift button. I'm not sure where my camera is. Yeah, you can use the shift button. Then you should find a button that says like STO. For me, it's like my RLC button, somewhere about that, hopefully. If you press that and then you press any one of the letters, like the alphabet letters on your calculator. So for example, I've got like A, B, C, D, etc. If you press any one of those, you should see a little number pop up the top that says like answer has been saved to A. If you do that, you can then come back to it later, and it's a whole lot of help. Other quick side note, because we're using a lot of scientific notation, if you find the button that says like ENG on your calculator, once you've got an answer like active on your calculator, you can press the ENG button and it'll slap it into scientific notation form. So you don't have to sit there and count up all the zeros. Which funnily enough, I didn't actually know that that button existed during my HSC. I found it during like the first week of uni, and I was devastated because I spent my entire HSC counting up zeros to do scientific notation, which sucked. But yeah, anyway, back to the question at hand. We now know what our force due to z is. We want to calculate what the current in x is, and to do that, we kind of need to extrapolate out our force due to x. Now, I'm going to quickly get rid of some of this stuff. If you want to, you can flick back a couple of frames on the video and save it wherever it was. But hey, it's a recording. This is one of the advantages of a recording, I guess. You don't have to worry about making sure everything's available live. Okay, let me flick back to my pen and let's do the second half of the question. So we now want to figure out what the force due to x is, and we said that the force due to x is equal to the force due to y, which we calculated as 2.67 times 10 to the negative 4. One more side note, I know that I wrote this as 2.67, it's 2.6666666666 repeating. Keep it in exact form. Don't round it, like actually on your calculator, keep it in the exact form. That's why I like to save it. Don't rewrite this in your calculator as 2.67. It means you may make mistakes. Don't round any of your numbers until you get to the very end. If you wanted to be using really actually good technique, you could write this as 2.6 and then just like ... times 10 to the negative 7. I'm just lazy is essentially what's going on here. Now our formula for fx is mu naught on 2 pi times the current in x times the current in y, all divided by our radius as being equal to 2.67 times 10 to the negative 4. You can rearrange all of this to solve for our current in x. So rearranging that gives us our Ix is equal to 2 times pi times our radius times 2.67 times 10 to the negative 4, all divided by mu naught, all times our Iy. And so now we can just start subbing some numbers in. So we can have our 2 pi times our radius, which is that our radius in this case is 35 centimeters, 75 centimeters, which we can convert into meters as 0.75, times our 2.67 times 10 to the negative 4, all divided by mu naught. Remember, mu naught is equal to 4 pi times 10 to the negative 7. This time, I mean, yes, I know I could simplify it as like 2 times 10 to the negative 7, whatever. This time I'm not, I guess. And then our Iy is 20 amps. So you can chuck that into your calculator, all of those numbers. Let me clean this up a little bit, but you can chuck all of that, chuck it in your calculator and see what you get. So 2 pi times 0.75 times 2.67, except I saved it before, so I'm going to use the exact answer, times all divided by 4 pi times 10 to the negative 7 times our 20, which if you do all of that, you end up with a current of 50 meters. 50 amps. I don't know why I said a current of 50 meters. Our current is 50 amps. And there we're done. We can kind of combine these two parts of the answer together. We can say it's 50 amps moving to the right. But that right there is our current in X. So just to sort of recap what we did, we first of all used what we know about attractive and repulsive forces in currents, between currents between two wires. And we used that to sort of figure out what direction this force needed to be. We used the fact that there's no net force on Y, and the only possible force that we could have was the force due to X to figure out, like, okay, it needs to be an attractive force pulling us up back towards X. And then we used our formula. We used the fact that these two forces have to be equal, and we used that to calculate our current. Hopefully that made a little bit of sense. Here's another slightly more detailed answer on my slides. But let's keep on moving along. So one fun little thing is this force that occurs between two parallel wires was actually originally used to define the ampere, which is a lot of fun. So the ampere is that this is like the formal funky definition. So that's why it's kind of whack. But getting on our best voice, we can say the ampere is that constant current which, if maintained in two straight parallel wires of infinite length placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 times 10 to the negative 7 newtons per meter. That's all to say, basically, it's the current that if you have two wires a meter apart, it would give you a force of 2 times 10 to the negative 7 newtons per meter. Because like in the formula, right, if you do mu naught on 2 pi times 1 divided by 1, it just gives you mu naught on 2 pi, which you may remember is 2 times 10 to the negative 7. Funnily enough, we actually got rid of that. It's not defined like that, which is funny because it basically, they changed it pretty much as soon as the syllabus changed. So we're only 3 or 4 or 5 years into the syllabus and it's already wrong, which is hilarious. But it's hilarious for us to laugh at NASA for having wrong stuff in the syllabus. However, it also shows you like science does actually change. Science is a dynamic field. There is stuff happening. And, you know, at the moment is an exciting time for physics. There's a lot of fun stuff that's actually happening in physics. It's a cool field to be involved in. So you guys have picked the right choice with your topic. So yeah, the ampere is now defined by taking the fixed value of the elementary charge, where 1 coulomb is 1 ampere per second, which is pretty cool. Okay, that's all on the motor effect. So just to recap so far, right, we've got electric fields, the things that are around anything that has a charge. We've got magnetic fields, which is produced whenever a charge starts to move. We've got the motor effect, which is whenever we have a current in a magnetic field. And now we're moving on to induction. Now, I'm not going to lie, I reckon induction, or at least parts of induction, are some of the hardest in the syllabus, at least the hardest to wrap your head around. So if you don't understand all of this just by watching your this video, don't worry. I was very much there. I don't really think I understood a lot of induction even by the end of year 12. It took me quite a while to wrap my head around stuff like Lenz's law. So it's a little bit of a whack topic. So yeah, don't worry too much if you feel a little bit overwhelmed just by this section. It is a perfectly normal feeling. You are normal. Anyway, what is electromagnetic induction? There's this guy, James Faraday. I actually don't know if his first name was James. James Maxwell. Sorry, I saw the word Maxwell, and I know Maxwell's first name was James. Not sure what Faraday's first name is. Either way, Faraday discovered that when he passed a current through a coil, a small current appeared in adjacent coil. It turns out he could get the same effect by moving a magnet. Just to recap that, basically he set up this little current, he set up this little circuit down here, and he noticed that when he turned the current on, in his circuit, and just to be very specific, this is sort of two separate circuits. Maybe to draw it slightly more abstractly, you've got your battery pack over here, you've got a little switch, and then you've got just your current here, and then this is a little ammeter, a little thing to like measure the current. And he noticed that when you close the switch, very briefly, you measured a little tiny current over here. It didn't stay constant. It was just sort of like you close the switch on one side and then the current just like briefly flicks. You get a little tiny bit of current on the other side. Um, and eventually, this was later measured by our favorite friend James Maxwell as Faraday's law. Maxwell's not going to be our favorite friend until Module 7, though. But once you get to Module 7, we love him. We stand Maxwell. Okay, and we call it Faraday's law. They're both very cool. Now, electromagnetic induction is defined as when a conductor exposed to a change in flux induces an EMF. Yuck. All right, there's a couple of things that we need to dig into. What is a flux and how do I use it? And what is an EMF and what the hell happens there? So, first of all, answering the first of these questions, what is a flux? Flux is defined as how many things are going through an area. So you can sort of imagine the flux of, say, a room of people is just how many people are in the room. So if we have, a big auditorium, it's probably got a higher like flux of people than, say, a car. There's only going to be one or two or three or four people in a car, whereas a big auditorium probably has a lot more people. Whereas flux density is basically how packed these things are. That determines what we call the field strength B. Now, another way of thinking about flux is you have a whole bunch of things, but then oftentimes you kind of need to force them through a very, very small area. Like you can imagine if you've got your big auditorium of people and there's a fire evacuation alarm, you've only got like that little tiny like doorway of space for stuff to go through. And so as a result, you're trying to squeeze a whole lot of people into a very, very small area, and that is going to cause some interesting squeezing problems. Now, in for the purposes here, we don't really care too much about like people and the flux of people. What we're interested in is what's called magnetic flux, which is basically just a measurement of how many magnetic field lines are in a particular area. Basically, how much strength of magnetic field is in a particular space. So down here, I've drawn two little areas. You can sort of see how in both of these situations, the amount of magnetic flux in both of them is exactly the same, right? They're both capturing they're both capturing four magnetic field lines. However, there is a key distinction between the two, which is that you can see in one of them, all of the field lines are nice and packed tightly in together, whereas in one of the other field lines, they're really quite spread apart. And that's because even though they both have the same flux, they do not have the same flux density, because flux density is how tightly packed those two things are going to be. So going back to the auditorium example, even though you might have like, I don't know, 100, if you imagine like an auditorium versus a car, you can fit you can fit maybe 10 people into both of those cases, right? But in a massive auditorium, 10 people is going to feel much less dense than trying to fit 10 people into a single car, right? And only one of them is going to get you arrested by the New South Wales police. Um, I mean, it depends. Yeah, anyway, I'm not going to get into that. So yeah, the flux is how much stuff is actually in an area, whereas flux density is how packed those things are into that particular area. That's what flux is. That's what magnetic flux is. But what we're also interested in is, well, what's an EMF? Now, the definition of EMF is electromotive force, but for our purposes, it's basically a voltage. Like it's measured in volts for our purposes. So you can basically read this as a voltage. And in fact, because in like 97%, I know I keep on using these really specific high numbers, but in like 97% of cases, when you read EMF, you can basically just read it as current. It basically means that there's some kind of current induced. So electromagnetic induction, to sort of put it in kind of layman's terms now, electromagnetic induction is the effect that occurs when you have some kind of wire exposed to a change in the magnetic field lines around it that induces a current flowing through it. So flicking back a couple of slides, we can go back to this situation and we can see what was happening was when you turn the current on in this field, suddenly we have some kind of current flowing through the wire. And because we know from our right-hand grip rule, that's going to induce a magnetic field. When we turn the current on, we go suddenly from having no current to having some current, which means we go from having no magnetic field to having some magnetic field. That is a change in magnetic flux because we go from having no magnetic field lines to having some magnetic field lines. And based off electromagnetic induction or Faraday's law, that says that should induce an EMF, which in this case, because it's a nice closed loop, is going to like manifest itself in the form of an actual current, which is a lot of fun. Um, so yeah, so for most of our purposes, it's a voltage, which most of the time will just be a current. So to recap, previous slides, our magnetic flux is the amount of magnetic field, which is basically just us counting the field lines, whereas our magnetic flux density is how like much magnetic field is in there per unit area, which is basically just how densely packed the magnetic field lines are. And as it turns out, our magnetic flux density is actually the magnetic field that we've been talking about so far, right? That magnetic field is measured as like our B, which means we can actually use this to kind of come up with a formula to calculate magnetic flux, right? Because if our magnetic field is the magnetic flux per unit area, i.e. B is equal to how much flux we have, and sorry, that was a horrible flux sign, how much flux we have per unit area, where this is like our area down the bottom, we can rearrange this formula to get that our phi, our magnetic field flux, is equal to magnetic field times by our area. And that is what we find out is exactly the formula down below. Our magnetic field is equal to phi divided by A, and our flux is equal to the magnetic field times by our A. Now, I'm not sure if I said it explicitly, but this Greek character is called phi. It's the Greek letter phi. We're going to use it a couple of times in the next few modules for various things, but it's just a circle with a line through the middle. It's nothing too fancy, and it represents our magnetic flux. Now, our magnetic flux density is, sorry, I should just call it our magnetic field. Is measured in Teslas as always. Our area is measured in meters squared, and then in my opinion, I reckon flux kind of takes the cake for the funniest sounding units that we're going to deal with in physics. But it's measured in Webers, right? So our little shorthand for it is WB. The longhand is Weber, or maybe Weber. I promise you, it's not one of those like little tiny cook stoves or whatever, barbecues, but that is the units that we're going to be dealing with. Now, the formula that you are given on your formula sheet is this full one. Once again, just ignore the theta, or try and ignore the theta. Once again, we sort of get a maximum flux when a magnetic field is passing through a particular area perpendicularly. And so as a result, I like to, if you're going to include the theta, I kind of prefer to think of it as be a sine theta, where theta is the angle between kind of the plane of your surface and your magnetic field. Because in the way that it's written at the moment, what this theta actually represents is if you have some surface, if you imagine you have a normal to the surface, if you can kind of pretend you've got some angle sticking up perpendicularly to your surface, that's what a normal means. It basically means if you've got like a flat area, if you've got something that's like sticking out perpendicularly to your surface, that's what we call the normal. The angle here, this angle theta, is the angle between your magnetic field lines and your normal. Not with your surface, with your normal. It's basically the angle between these two. Which, like, if you think about it for a second, like it does kind of make sense. Because it means that you then have zero when the normal is parallel to the magnetic field lines, which is the same as having the magnetic field lines going perpendicularly to the surface. But just like in that case, do it perpendicularly to the surface and use sine for the first case. Anyway, all that being said, you will get a maximum, you have maximum flux passing through when you have a like perpendicularly, basically. Um, so yeah. The other way it's kind of written on your formula sheet is you have perpendicular magnetic field. Sorry, you get a maximum flux when your magnetic field is perpendicular to your area. So let's actually jump into this question. I've done enough ranting at the formula. Let's try and actually do some stuff. As always, you can do the practice if you want to down below. I really encourage you to because it will mean that you'll like digest it a little bit more. Okay. Um, so we're trying to calculate what our magnetic flux is. Basically, we're trying to figure out what is our phi equal to. Um, we know that the magnetic field has a magnetic field strength of 3 Tesla, so let's jot that down. Our magnetic field strength is, I just wrote T, it's 3 Teslas. Um, and it's in a circular coil with a radius of 2 meters. Basically, we've got some kind of circle with a radius of 2 meters, and we need to calculate the area of this, right? Because we want to know how big is the space of this coil. So in order to do that, we're going to use the formula. Our area of a circle is pi r squared. So chucking in r, we get our area of the circle is pi times 2 squared, which is equal to 4 pi. You can evaluate that on your calculator, but just for the sake of like, look, I'm a math student, I like to keep things in exact form. We can write that as like 4 pi. And then finally, we can chuck this into the formula. We get our phi is equal to 3 times 4 pi, which is equal to 12 pi. Which, you know what, let's chuck it into the calculator to get a feel for how big that is. That is 37.699 Webers, or Webers, or however it's pronounced. But yeah, that's how we calculate our magnetic flux. However, that was only half of the definition, right? The other thing that we had to deal with was EMF, and just like flux, we actually have a formula for EMF as well. Now, Faraday's law states that relative motion between a conductor and a magnetic field induces an EMF. This is just a fancier way of defining the electromagnetic induction that we dealt with before. It's a slightly more rigorous definition. It basically just says that you can kind of interpret it in the same way, right? So beforehand, we said that any kind of change in flux, any kind of change in magnetic flux is going to induce an EMF. This is basically just saying that instead of saying a change in flux, it's saying a relative motion between a conductor and a magnetic field, which they may not seem it, but they mean the same thing, right? Because a change in flux is basically you've just got some kind of change in magnetic field. This is basically just saying like if you change something between a conductor and a magnetic field, it's going to cause a change in flux, and so as a result, it's going to cause an EMF. Now, the size of that induced voltage is directly proportional to the rate of the size of the magnetic flux. Basically, you have this formula here. Now, if you've never seen this little like half or 3/4 infinity sign, it basically just means proportional. If you're not super comfortable with the idea of proportional, it basically just means the only thing that's left is some kind of constant or some kind of like proportionality thing. So we could kind of write the full formula as being epsilon is equal to minus n delta phi on delta t. Where n is some number, but it actually turns out that it actually does have a particular use in this case here. Now, a couple of quick notes. First of all, if you do advanced maths or pretty much any level of maths aside from standard, this delta phi on delta t, you can actually interpret this like just intuitively. You can remember this is actually a derivative. It's basically like the real formula has a derivative in it. It's just that because we are a no calculus course here in physics, we want to make every excuse to not touch on calculus, so we make the delta phi on delta t. But for example, if you have a question that's asking you to like draw a graph of to like sketch out or like identify which graph has the flux, you can just remember it's the derivative, so we're dealing with gradients instead. Um, if you don't do advanced maths, that's fine. You don't have to worry about it because like it is designed so you don't need to know that it's derivative. I just find that if you do know it's a derivative and you like derivatives, I prefer to think of it that way. The other thing to make note of is the negative. Um, It basically is because of the law of conservation of energy. It means that stuff doesn't die, and we'll talk about it a bit more in just a second. But here is a lovely little moving picture that some pronounce GIF and some pronounce GIF. GIF is the correct pronunciation, by the way. That sort of shows us what's going on. So you move a magnet inside some kind of coil, and it will induce a voltage as a result. Um, yeah, we'll dig into it a little bit further in just a second. Um, Now, sorry, I thought I did have it on my slides, but the full formula is, and the formula that you're given on your formula sheet is epsilon is equal to negative n delta phi on delta t, where epsilon is our EMF. Um, Epsilon is our EMF, which is measured in volts. N is the number of coils in our is the number of coils in like whatever thing we're inducing a current in. So for example, here you can see that there are a whole bunch of coils. You would just count them up, and however many there are, that's your value of N. Delta phi is how much flux is changing. So I'll show you how to do that in the next example, but usually it's going from like some very small amount of flux to some quite high amount of flux. And then our delta t is whatever change in time is occurring. Basically, like how quickly are you doing it? Are you doing it over the course of 2 seconds? Are you doing it over the course of 0.02 seconds? Like what's going on there? And then the negative is just a negative. The change in phi is measured in Weavers, and the change in time is measured in seconds. I think that's all we need to talk about here for this formula. This formula, sorry, and the reason I bring that up is because this is the formula that is on your formula sheet. Epsilon equals negative n delta phi on delta t. You should be able to find it in the electromagnetism section. So let's jump into a cheeky little practice. The diagram shows an electric circuit in a magnetic field directed into the page. The graph shows how the flux flows through the conductive loop. The flux that flows through the conductive loop changes over a period of 12 seconds. And we want to calculate the maximum induced EMF within the stationary loop during the 12-second interval. Basically, we want to figure out what is the biggest EMF that we can possibly induce here. Now, one of the reasons that I like to think about our formula as as a derivative, I'll show you in just a second, sorry. But basically what we need to do is we need to look at our graph and we need to figure out, okay, whereabouts are we going to get a maximum EMF in? And the reason that I like to think of this as a derivative is because a derivative just tells us about the gradient, right? The derivative of a graph just says that what we're looking at here is not the actual thing itself, but what we're looking at is the gradient. Now, in order to get the maximum, that means what we're looking for is we're looking for the point where the gradient is the most shocking, basically where the gradient is the steepest. So in this case, you can kind of spot there's three different sections to the graph. We've got this section here where it's kind of sloping upwards. We've got this section over here where it's a bit flat. And then we've got this section where it suddenly drops from a very high value all the way back down to quite a low value in a very short period of time. So just looking at this graph, the like sharpest peak, the sharpest gradient occurs in this last section over here. This is where we've got this really, really sharp drop. So just in terms of looking at this visually, the highest gradient, the biggest gradient is occurring in this section here. So if we're looking for the maximum induced EMF, we're probably looking at this section here. In this case, it is the correct answer. We are actually looking over here, but I just want to pause for a second and I want to say, be careful when you're doing questions like this because of this negative, right? If we are looking for the maximum number, we're looking for the largest positive number. And what you may have noticed over here is that this gradient is actually negative. It's sloping downwards. So if our formula just was like calculating the gradient, this would actually probably give us our lowest possible EMF because it would be a very large but very negative number. And so our maximum EMF would be over here. As it turns out, the formula actually bungs a negative out the front, like we have this negative chilling out here, which means that when we calculate this negative gradient, we then slap a negative out the front, which turns it into a positive number. And so as a result, our net EMF is actually still going to be positive, which is quite lovely, which is exactly what we want. So we can chuck all of that into our, now that we figured, sorry, that was all to say essentially, in this case, our maximum EMF occurs at this point here because it's the steepest gradient, but also because it's negative. So in general, if we're looking for the maximum possible EMF, we're looking for the steepest negative sloping section. However, it's important to always read the question carefully because sometimes it might just be looking for the maximum magnitude of EMF, in which case it could be like this section over here if it was steeper because the absolute value of that particular EMF would be larger. Okay, that all being said, we finally actually know like what the change is going to be. We finally know which region we're actually analyzing, which is this section over here. Now let's actually get to plugging some numbers in. Let's try and calculate this thing. So we've got the negative. We know that this is a single loop. We're told it's one loop, which means that our n is equal to 1, and like the diagram shows that as well. It's just n equals to 1. We then just need to calculate our change in time and our change in flux. Now, looking at the diagram, the period that we're analyzing is this period between 10 and 12 seconds. So hopefully you can think that our delta t is going to be equal to 2 seconds. That's just the way it is. You could calculate that, of course, by doing 12 minus 10, which is equal to 2, but it's still just going to be 2. Trust me. Then our other thing that we need to do is we need to calculate our change in flux. Now, remember, just as a bit of a side note, this is true for physics. This is also true for chemistry, true for, I don't know, it might be true for bio as well. It's always true, but like, I don't know if you'd use it in bio. But whenever we're calculating a change in something, what we're calculating is we're doing the final of that thing minus the initial. So in this case, we're doing the final flux minus the initial flux. And in our case, our final flux is equal to 0 minus our initial flux, which is equal to 0.6, which if you chuck that on, you can do it in your head. That gives us a change in flux of negative 0.6. So finally, we've got our number of coils as 1. We've got our change in flux is negative 0.6. And we've got, I forgot to write it, but our change in time is equal to 2. So suddenly, we can chuck all of this onto our calculator. We can say our epsilon is, our EMF is equal to negative of 1 times our change in flux, which is minus 0.6, all divided by our change in time, which is 2, which if you chuck all of that onto your calculator, you end up with an EMF of 0.3 volts. And I'm very sorry, I realized I never said it, but this funky looking backwards E thing is what we call epsilon. It's the Greek symbol epsilon. But yeah, so we've got a maximum EMF of 0.3 volts, which is lovely. So that being said, that brings us to what, in my opinion, is probably it's probably the hardest concept of this module and one of the hardest concepts in the entirety of physics, which is my favorite law, my least favorite law, Lenz's law. As Lenz's law says, an induced current must flow such that it creates a magnetic field that opposes the change in flux. Basically, this is where the negative in Faraday's law comes from. It basically tells us that if we have a change in flux, basically if we have a current flowing in one direction, the current that's induced in the other side always needs to oppose it. Whatever changes needs to be acting in opposition. And this essentially comes from the law of conservation of energy. Now, to understand where this comes from, let's do a cheeky thought experiment. So let's imagine what happens when we move a coil of wire through a magnetic field. Now, by Faraday's law, we are going to induce some kind of current. Now, by Lenz's law, the negative, the EMF is going to oppose the motion of the wire, and so basically over time that current is going to dissipate out to nothing. So essentially, we move the current into the wire, and sorry, yeah, we move the coil into the wire. Sorry, let me express this better. You move the coil into the magnetic field, and by Faraday's law, a current is induced. And by Lenz's law, that current is acting to like oppose the motion of the wire. Basically, if you remember back to the motor effect topic, the current that's flowing through the wire is going to induce a force, and Lenz's law basically just says that the direction of the current is going to be such that the force is acting in opposition to whichever direction you're moving the wire. However, to see sort of why that's important, let's imagine what would happen if the current instead supported the change, basically went in the same direction. Well, if the current supported the change, we would get like even more current because we're moving it even faster through the current. So it would move faster, so we'd get a greater change in flux, so there'd be more current, so we would have suddenly infinite energy, and like, yeah, we've just solved climate change, and oopsie doopsies, we've just made a black hole, and bada bing, bada boom, we've just destroyed the universe. So basically, the law of conservation of energy here is just coming in clutch to save our lives, which honestly I stand, big fan. Um, so yeah, so Lenz's law is always working to kind of oppose whatever change is happening, and it means that stuff is always going to be not going bazonkers, which big fan. And yeah, um, so let's do a cheeky practice here. Let's try and figure out what what direction is the current going to be induced in the room? Is it going to be clockwise or is it going to be anti-clockwise? So in this situation here, we've got a ring that is being pulled out of a magnetic field. And we need to figure out, well, by Lenz's law says, okay, we need to oppose whatever change is happening. We kind of need to go from this very concrete example, apply that slightly abstract law, and figure out, okay, what is actually going on here? Okay, now the way that I would encourage you to do this is to sort of break it into two steps. So your two steps are going to be, first of all, identify what the change in flux is. So identify, and I told you before, my writing is horrific when I'm trying to write as I'm writing. So identify the change in flux. Figure out like what is that change actually going to be, and then once we've figured out that change in flux, use your right hand grip rule. Right now, a lot of people will say just use your right hand ruler. And while, once again, with the very specific percentages, maybe like 5% of cases you might need to use your palm rule, all of the other percentage cases, you're going to be using your grip rule. So use the right hand grip rule. Hand grip rule. Yes, because in this case, most of the cases we're going to be using right hand grip rule. To go back to like what I sort of started saying earlier in the lecture, in general, you use your palm rule whenever you're dealing with forces. You use your grip rule whenever you're dealing with currents, or the relationship between currents and magnetic fields. You could also sort of think of that as like you use the grip rule whenever you've got a circle. Whenever there's anything that's in a closed loop, you're probably going to be using the grip rule because like the grip rule moves around in a circle, so it sort of checks out. That's why we use the grip rule there. So in this case, we've got our ring, we're moving it out of a magnetic field, and the first thing we need to do is identify that change in flux. Like what is actually happening? What change in flux is actually going on here? To do that, let's break it down into two situations. Initially, we've got some kind of magnetic field that's going into the page, and then afterwards, we've got no magnetic field that's going into the page. So from the perspective of the coil, we started out with a magnetic field. We then don't have a magnetic field anymore, which means the change in flux is we're losing this magnetic field. Okay? Hopefully that makes sense so far. So we've gone from having no magnetic field to having some magnetic field. Now, here's the step that most people struggle with, which is how do we kind of oppose that change? What can we do to actually like cancel out whatever change was happening? Well, if we lost a magnetic field, the way we can cancel that change is we can reinstate the magnetic field. We can add it back. We can kind of make a fake version of a magnetic field moving into the page. Hopefully that made a little bit of sense. Basically, to recap that, right? We started off with a magnetic field, we lost it, magnetic field disappeared. So to oppose the losing of the magnetic field, like we're trying to oppose the change, which was the magnetic field going kapush. In order to oppose that change, we need to add a magnetic field back in. We basically just need to add these x's back in. And that is our change in flux done. We've identified the change in flux. I should probably add on, we need to figure out like how to oppose that change. But now that we've figured out how to oppose that change, all we need to do is use the right-hand grip rule. And the right-hand grip rule that we're going to be using is on this magnetic flux that we've just drawn down here. So we've got a whole bunch of field lines going into the page. We can just use your right-hand grip rule on those field lines going into the page, right? So just a side note, the right-hand grip rule is kind of reversible, so you can it's not strictly like thumb has to be one thing and fingers have to be the other. You can kind of just use it with whatever you've got can be one of them, and whatever you've got can be the other one. So in this case, we've got a magnetic field with your thumb pointing into the page. So you can use your fingers to represent the direction of the current that's going to be induced as a result. So you can point your thumb pointing into the page, your fingers can be curling around, and if you do that, you'll see that your fingers curl around in a circle like this, which is pointing in the clockwise direction. And that is how we do this question to apply Lenz's law. So just to recap everything that's going on here really quickly, because I know that a lot of people will really struggle with this. The first thing we did was we identified the change. We said, okay, what was happening? We went from some magnetic field to no magnetic field. Therefore, the change was we were losing our magnetic field strength. That's step one. Step two, we then ask, how do we oppose that change? All right, so we start off by having the change, which was we were losing our magnetic field. Then we needed to oppose it, right? We needed to stop that change from happening. So in order to oppose that change, we sort of reinstate the magnetic field. We add it back. We create our own fake magnetic field instead. So that is what we're trying to do here. And then once we've created that like fake magnetic field, we use our right-hand grip rule to figure out what is the direction of the current that's induced going to be. And so in this case, use your right-hand grip rule and you find out it's going to be pointing in that anti-clockwise direction, which is very, very lovely. Okay, well, that brings us in just over 2 hours to the end of block one. So I had vaguely thought that maybe I'd be able to get through everything. I highly recommend them. Before we move on to a last little bit of more module 6 that we should get to, I just wanted to go through some quick study tips to sort of explain some of my tips as how I would recommend you could go about studying for some things in physics. So firstly, like how to actually approach a question. So problems in physics tend to fall into one of 3 different categories. You've either got calculations, you've got explanations, or you've got regurgitations. And they could also be a combination of some, like it seems like in the new syllabus, they really like to have extended responses that are sort of combinations of particularly the first two, calculations and explanations. But I would encourage you, you can kind of, if you like to be a bit analytical in the way you study, you can kind of split each question that you study, each question that you do into like one of these. Calculations, probably the most obvious questions because they're just like you have to calculate something. So my tips for this is know your formulas. So really know your formula sheet kind of in and out, which is why I say if you're not familiar with your formula sheet already, this is your opportunity to do so. The formula sheet is what you're going to be taking into your final HSC exam, so I would really, really encourage you to know it very, very well. If possible, try your hand at trying to derive most of the formulas on your formula sheet, because that will sort of show you some of the links between different formulas and how they work together. You can't derive every single formula, but particularly in like the gravity topic, there are a lot of the formulas that you're able to derive. And then the other key thing with calculations is just to practice them. There's really no substitute for just practicing your calculations over and over and over again. It will get you to really know your formulas. It will help you to really like understand how they link together, what some of the common things are that they link together with. And yeah, it will really help you to smash out all of your calculations. On top of that, just some smaller tips. You can do stuff like write down all of the info that you're given in a question. You can set it all out. You can. I really encourage you to highlight like what the thing is that you're looking for. So, for example, if you're asked to calculate, you know, the magnetic field force, you write down I need to find magnetic field force, and then you can kind of build like a bit of a search tree, right? Because you can be like, okay, I need magnetic field, which means let's write down the formula for magnetic field force. So that's going to be I, or like you could write down it could be ILB sine theta. It also could be QBB sine theta. And then you might be, okay, I know what B is, I know what L is, but I don't know what I is. Okay, what formulas do I have for I? And then so on and so forth, right? And just keep working your way down until you have all of the pieces that you need to find. Um, and yeah, that's how I'd really encourage you to go about studying your calculations. Um, they really are just about doing as many of them as much as possible, and that will really solve a lot of your struggles with calculations. Because a lot of them are reasonably straightforward. Okay, then we've got explanation. So explanation questions are basically where you're given some kind of situation and you have to use your understanding of physics and your understanding of different laws and how things relate to each other, and you actually have to explain what is going on in a particular situation. Now, in my opinion, some calculation questions can get very spicy, but oftentimes the hardest questions in an exam come from explanations, because in order to do it, you need to not only like really understand all of the physics concepts, but you need to be able to identify and like be able to use them in an unknown situation. Now, a couple of tips that I would have for this is just like be engaged in physics in the wider world. So what I mean by that is like use the stuff that we've been learning and try and like ask questions about like how they apply in the real world. And like just when you're living your everyday life, maybe think about, oh, like this kind of relates to something that I did in physics. So for example, if you're on the like on the bus or like driving your car somewhere and you go around a corner, you can kind of think, oh yeah, like uh this kind of, it's like circular motion. If I go around really fast around a corner, like I get kind of shoved into my seat a little bit because force is equal to mv squared on r, and so if I go much faster, i.e. I have a larger velocity, then I experience a much bigger force. Because that's the sort of the reason I say that this is like one of the best ways to prepare for your explanations outside of just understanding your physics concepts good, which like I probably should say like the best way to prepare for physics stuff is just to understand and know how things apply and be able to solve the problems. But like in order to get used to just applying physics concepts to new scenarios, just like play around with them in your real life, right? Because as shocking as it may be, physics is the hidden laws that like surround us at all times. So there is always physics surrounding you every moment of every day. Um, Sorry, oh, that went down. Um, of course, then the other way to sort of get better with it, just like with calculations, is just to practice. If you do a lot of practice, and when I say practice, I mean practice questions, practice papers, topic tests, the questions in the back of your textbook. Actually, let me organize that a bit better. When I say practice, first step when you learn a concept is just do whatever questions the teacher's given you, and then maybe do the questions in your textbook. Once you've got those on a grip, do some kind of topic test, whether it be like the thing at the end of each chapter of a textbook, or I can recommend the 8 onwards topic tests or something like that. And then once you've got that under wraps, that's when you should start moving on to like past paper questions, trying to do like sit through different past questions and stuff like that. Because those will often be a little bit trickier, so you don't want to really dive headfirst into those ones right off the gate because you'll probably struggle and they'll be hard and you'll want to cry. So yeah, just a lot of practice is the best thing. The reason practice is so good is because physics is a practical course. Like it's all about learning these things and understanding how they apply in the real world. So the only way that you can get used to applying them in the real world is by practice using them in the real world. Then there's regurgitations, which is, I don't know, it's simultaneously like the easiest because in a sense it's just like word vomit of stuff that you've learned in the syllabus. But on the flip side, um, I probably like them the least because it's scary because you have to write well and I hate English. Um, but basically, the way I would encourage you to do this is just know your content. This is kind of where it comes down to just knowing a whole bunch of stuff. You wouldn't have encountered, if you've only done module 5 and module 6, you haven't encountered many of the really content heavy dot points just yet. Probably the closest you may have come to it is like in module 5, you will have done the thing on like different satellites and different satellite types. It's the kinds of questions would be like, what is a geostationary satellite and what does it do? It's where you're just basically giving your definitions. So I would encourage you for these ones to sort of practice structure, practice your nomenclature. This is where I was talking about jargon beforehand. Jargon will come in really handy for not having to write as much, which is lovely. Oftentimes it's about like giving cause and effect and stuff like that. So yeah, once again, practice is very important, and this is where you can sort of go through by the dot point to like the dot points of the syllabus and be like, oh, okay, do I really understand this? Do I feel like I have enough to write like 6 marks on this specific dot point? Is probably a way that I would encourage you to like benchmark yourself with this one. Um, Lovely. Well, all of that out of the way, we've got a couple of minutes left to just start on our applications of induction. So the concept of induction is very, very important and has a whole bunch of applications. The syllabus asks us to look at 2 specific applications, which are transformers and electromagnetic braking systems. It also is very important in motors and generators, which I don't think we'll get to, but you've got the slides, so if you're interested, you can look ahead on the slides. So let's firstly take a look at the idea of eddy currents. Eddy currents are circularly induced currents that sit on the surface of flat conductors. Basically, what that means is that when you have a big sheet of metal and you pass a magnet over it or some kind of magnetic field passes over it, Lenz's law, remember, Lenz's law said that if you have a conductor and you have a change in magnetic field, that's going to induce an EMF. The difference here is that because rather than it being like a coil, it's like a massive, big, proper sheet of metal. When you induce a current on it, the current kind of doesn't know where to go, and so as a result, it will move in a circle. And that circle is what we call an eddy current. Um, yeah, so it's theoretically nothing new. It's just Lenz's law being applied to rather than a circle, sorry, rather than like some kind of circuit, it's being applied to like a full big massive sheet of metal instead. Yeah, so that's what an eddy current is. Now, it's going to be used, in this first example of electromagnetic braking systems, it's sort of the goat of electromagnetic braking systems. It's what we want. However, it's kind of annoying because it then means that if you've got a sheet of metal and you have a magnetic field passing through it, sometimes you accidentally get a current flowing through it, which might not be great if you don't want that current to be flowing through your metal, as we will see in transformers. So an electromagnetic braking system essentially works by having an electromagnet passing over some kind of wheel. So you can kind of imagine that this triangle here, sorry, triangle, you can tell I've been speaking for like 2.5 hours. This rectangle here, sorry, you can kind of imagine is like a side-on view of a nice circular or cylindrical wheel. So imagine that this is not a great drawing, but imagine that this is just like a side view of our wheel. You slap the electromagnet on the sides of the wheel, and that passes some magnetic field through the wheel. And then as the wheel spins, from the perspective of like a little piece of metal on the wheel, it then enters into the magnetic field on one side and exits out the magnetic field on the other side. Which means, remembering back to Lenz's law, we have some kind of change in magnetic field as we're passing through, which means we've got some kind of change of flux as we're passing through, which means we are going to induce some kind of current. And as that current that we're talking about is going to be that eddy current that we're dealing with over here. And yeah, so that's essentially how we're going to induce eddy currents. So to recap, we've got an electromagnet over the top of our metal wheel. As the wheel spins, it goes sort of in and out of the magnetic field, or like different points on the wheel will go in and out of the magnetic field. And so as a result, we will get these little currents induced on the surface of our wheel. And those eddy currents, they sort of serve 2 purposes. They will, first of all, just exist, which means they will like dissipate heat. Because they're currents flowing through a wheel, they sort of will like encounter resistances and they will turn into heat. And if you sort of think about the law of conservation of energy, that means we're taking the motion of whatever is moving the wheel and we're converting its kinetic energy into heat energy. We're sort of dissipating its energy as heat, which is going to slow it down over time because we're taking the kinetic energy and we're getting rid of it. We're turning it into heat. The other thing it's going to do is, because it's going to act by Lenz's law in such a way to oppose the motion, it's going to sort of induce a magnetic field to just kind of repel itself from like the electromagnet. And so as a result, that's going to sort of slow the wheel down because it doesn't want to spin anymore. It doesn't want to go through the electromagnet. And so that sort of aligns itself in such a way that it tries to sort of slow down. Now, just to do a little bit of practice, I might sort of end on this thing then, just so I can go into it in a bit more detail. Um, we can sort of analyze what's actually going on, and we can apply what we learned in Lenz's law to actually figure out like which direction are our eddy currents actually going to move. So imagine that you're a little spot on this wheel, and the green dots, by the way, are the magnetic field, like that's acting on our wheel. And you can imagine that you're a little dot on the wheel, and then you're slowly getting pulled in, well, not slowly, but like if you're moving really quickly, you're getting pulled into towards this magnetic field. Thinking back to our Lenz's law structure, right? The first thing that we want to do is we want to figure out like what is the change in flux? Well, the change in flux is we're going from having no magnetic field to having some magnetic field. Basically, we're gaining a magnetic field. Um, and Lenz's law says we want to oppose whatever change is happening, which means we want to oppose the flux that is like being created, which means we want to cancel it out, which means we want to induce a magnetic field that's acting in the opposite direction. So we could sort of say like our ideal situation is we want to have a magnetic flux that's moving into the page, right? It's going in the opposite direction to the magnetic field that we currently have, because we are increasing the flux, so we want to decrease it by like canceling it out. Now, once we figured that out, we've sort of done the hard part, and all we have to do is use our right-hand rule to figure out, well, which direction are the eddy currents going to be moving in. And if you do that, you find out, oh wow, look at that, your thumb's pointing into the page, your fingers are then all going to be pointing in the clockwise direction, which means, wowzers, we have a current that's moving around in the clockwise direction as well, which is very cool. So that tells us over in this direction, we've got a current that's moving in the clockwise direction, and we can do the same thing over here. So sort of like on the other side of the wheel as well. So imagine you're a point that's currently like inside the magnetic field, and then the wheel spins and you get pulled outside of the magnetic field. Well, that's also a change in flux, right? We've gone from having some magnetic field to having no magnetic field, which means in this case, the change in magnetic field is that our magnetic field has disappeared. But Lenz's law once again says we want to oppose that change in flux. We want to stop it from happening, which means we want to cancel that change in flux out. And the change this time was getting rid of magnetic field, which means what we want to do is we want to induce magnetic field, right? We want to create the magnetic field. So we want to make a magnetic field going out of the page, coming back out towards us. So once we figured that out, we want to have the magnetic field coming back out of the page towards us. We can use our right-hand grip rule, and you can point your thumb back towards yourself, fingers curling around, and we have an eddy current. We want to have eddy current moving around like that. So that basically tells us another way of thinking about that is that we're going to have an eddy current moving around, and I think I've actually got it on my next slide. We're going to have eddy currents moving in a clockwise direction on this side and an anti-clockwise direction on that side, which is going to induce exactly the magnetic field that we said that it was going to induce just beforehand, right? So it's going to be a magnetic field going into the page over here and a magnetic field coming out of the page over here. Let's pause for a second and think about what that actually represents. That means that as we're entering the magnetic field, basically on this side, we've got a magnetic field that's, so we're going to slow down. And so that's essentially how our electromagnetic braking is able to operate correctly, which is very, very cool. Okay. Yeah, so this slows down the wheel for two reasons. Firstly, the eddy currents will heat up the wheel, which converts its kinetic energy into thermal energy. And then also the eddy currents generate their own magnetic fields, which are going to oppose the wheel's load motion, which is what we saw over here due to Lenz's law. Okay, I've got like 4 minutes left. Let's speedrun just an elementary idea of what a transformer is. So a transformer is a device that either increases or decreases the voltage of an alternating current. Basically, you can have an AC voltage, and a transformer is something that will change it. It either steps it up or it steps it down, where a step-up transformer basically increases the voltage, and a step-down transformer decreases the voltage. Um, and yeah, so it's incredibly useful. It's a very, very important device because it's something that basically is the backbone of most of our modern power grid, because the voltage that is generated at the power source is probably not going to be particularly useful if you try and plug your laptop into a 1000 volt supply that's being generated off in a wind farm somewhere. It will probably explode your laptop. So instead, you've got to use a transformer that is going to step down the voltage. In fact, you potentially even have transformers inside your like charging cables themselves to like step up or step down voltages to give it just like to change the voltage from whatever the thing is that's coming in to perfectly whatever voltage you need that's coming out. So yeah, that's essentially why step up and step down transformers are important, is because like not every single electrical device needs exactly the same voltage. So instead we have to sort of wiggle them around a little bit. Now, one quick question I've got for you is just to think about is why do you have to increase a current to decrease the voltage and vice versa? Because a step down transformer is going to increase voltage and decrease current. A step down transformer is going to decrease voltage and increase current. If you want to pause the video and think about this just for a second, you can. But the answer is essentially because of the law of conservation of energy once again, right? We can't run away from that sucker. But it basically tells us that the power that we supply into a transformer has to be the same or more than the power that comes out of the transformer. Basically, we can't generate power inside our system. And if you remember, power is equal to current times voltage or voltage times current, which means that the voltage and current that we input, we could call it like the initial current, needs to be equal to the voltage and the current that we output, the final current and the final voltage. Which means if we increase voltage over the course of our transform, like our voltage number increases, because we need like the net change to not be there, in order to compensate for that, we would need to decrease our current as a result, and vice versa. Now, speedrun, 1 minute, how it essentially works is if you provide some sort of alternating AC current passing through the first coil, it generates a changing magnetic flux, which then passes through the second coil, and that changing magnetic flux, by Lenz's law, what we've been learning all about today, with our induction topic, that will generate a current in the second coil, which we can then, that will induce an EMF, which is a voltage in the second coil, and that's how we can transfer it across. And basically then we have these formulas that tell us what the relationship between all of our different things are, which is absolutely lovely, and allow us to manipulate the voltages inside of things. Anyway, I'm basically out of time. I'm very sorry that I didn't get through the rest of this. Transformers, there's sort of two things you can do with them just from an HSC perspective. You're going to need to know what your formulas are, and you're also going to need to know how to design transformers to make them really good, because the eddy currents that we were just talking about with electromagnetic braking, even though they were so important for electromagnetic braking, they are kind of very annoying for transformers because they mean that you lose power, which is not wonderful. So we have to do a bunch of stuff to fix them. And then the final topic for this module is motors and generators, which is kind of where we get into the dirty of like how do we actually use electricity to do some interesting stuff and do all of the things that we have seen so far. But anyway, I am out of time for today. If you want to, I would really encourage you to download the slides and go through the rest of it by yourself if you want to. But otherwise, thank you for sticking around for the whole video. I'm so sorry once again for not being able to do this one live. But I hope you have enjoyed the recording and you have learned something new. That is the goal. That being said, thank you all very, very much for watching. I will see you all again in another lecture. Have a great rest of your holidays. Do actually take a holiday at some point. Do have a little bit of break. I hope you're not studying 24/7. And I'll see you all next time. See you guys then.